Okay, 1 o'clock. So we are ready to start this symposium. So, um, dear colleagues, dear speakers, dear participants, I have the honor to express a warm welcome to all of you on behalf of the chairs of this Photocat symposium. That is my colleague, Professor Shubik Das, and myself. As we all know, photocatalysis represents a unique class of chemical transformations, utilizing the energy delivered by light and drives reactions that are difficult or even impossible to carry out in dark. So photocatalysis promises a sustainable solution to large-scale solar energy storage. And based on this, novel reactions and photocatalysts have been discovered recently. So with this symposium, we hope to highlight the recent advances in the domain of photocatalysis and their applications towards the synthesis of new complex molecules to fuel generations. The motivation to organize this symposium is to offer a nice opportunity for researchers working in the field of photocatalysis to meet and discuss virtually recent research results and future perspectives in this field. We hope also to offer a forum to young researchers like PhD students and postdocs in order to learn and to also participate in the discussions. And actually, we are very happy today to see the international set of high-level speakers that are willing to talk in the next days, and also the large number of participants. I think in total we reach almost 400 participants, so we are very happy about that. And of course, we had hoped to welcome you in person in Antwerp, but this is unfortunately not yet possible, so we will do it in this online format. I have to mention also that this symposium is co-organized by the Royal Flemish Chemical Society, the KVCV, and the Department of Chemistry of the University of Antwerp. And especially we want to thank the people from KVCV like Thomas and Mario a lot for their support with the organization and the technical support during the sessions. Now, before the kickoff of the first lecture, I have a few practical announcements for the planning of today and the coming days. So the talks are scheduled as 55 minutes per lecture, meaning 45 minutes actual talk and 10 minutes for the discussion. And if you have a question, please write your question in the Q&A session. And we will hope to be able to answer all questions that are formulated in the Q&A session. Now, if you are not a panel member, your microphone will be muted, but you can write a message in this Q&A session. So thank you very much for your attendance. So I look forward together with you to some exciting science in the field of photocatalysis. So let me now proceed with the introduction of the first speaker of today. So we will start with a lecture by Professor Masahiro Murakami from the Kyoto University of Japan. And he will talk on synthetic reactions driven by photon. Professor Murakami is currently a chemistry professor at the Kyoto University in Japan. He studied chemistry at the University of Tokyo, receiving his doctoral degree in science in 1984. Then he started his career with a research assistant position at the same place. And in 1987, he moved to Kyoto University to take a research assistant position there. He also worked in the period 91-92 with Professor Albert Eschenmoser at ETH Zurich as a postdoctoral fellow. Then he came back to Kyoto, being promoted as an associate professor in 1993 and a full professor in 2002. His research interests focus on the discovery of new, synthetically useful and mechanically interesting organic reactions. The utilization of photoenergy for organic synthesis is currently his major research topic. So please, Professor Murakami, the floor is yours. and we look forward to your lecture.
Thank you, Professor Ku, for your kind introduction. I also thank Shobik and other organizers for arranging this wonderful symposium online. Hello, everyone. Nice to meet you. Today's presentation is a significant challenge for me because I completely lost chances to speak English during the past 18 months. No overseas travel, no overseas visitors at all. It never happened in my professional life. So please allow me to speak slowly. Today, I share with you the recent result of my research under the title shown here. And I wish to modify the title a little bit. So today I focus on the reactions we developed using solar light as a driving force. I show you 7 examples which fit in this title. Now, first example, solar light assisted the production of dihydrogen gas. Mechanistically, the process consists of 2 stages. First stage is dimerization of aromatic ketone to produce diol. This reaction is nothing new. It has been known for a decade, or no, for several decades. When this aromatic ketone was irradiated with solar light, it dimerized to make this diol. We make this dimerization reaction practical by putting ethanol solution of this aromatic ketone in a plastic bag and put the plastic bag in a stainless container here, and simply put this stainless container on a rooftop on a sunny day, and we got this diol in almost quantitative yield as a diastereomer mixture. Now the second stage, production of dihydrogen gas. When this diol was treated with palladium carbon, this ketone was regenerated with evolution of dihydrogen gas. So there have been reported many reactions to pick up dihydrogen from ethanol, but this reaction is uphill in energy. But hydrogen is gas. So if you remove hydrogen from the reaction system, the reaction proceeds from left to right. But thermodynamically, this is an uphill reaction. But this diol is energetically higher compound. So this production of dihydrogen from this diol is energetically downhill, spontaneously occurring. So in the first stage, energy of solar light was utilized to pick up this 2 hydrogen from ethanol to put in a diol. Then in the second stage, dihydrogen was evolved from this diol to regenerate this aromatic ketone. So this aromatic ketone is recyclable. If this generation of dihydrogen was carried out in the presence of olefin, hydrogenation reaction occurs to give the saturated hydrocarbon in almost quantitative yield. So now you don't have to use a cylinder for the source of dihydrogen gas. This diol is solid, stable toward water and oxygen. It can be put on a shelf for months without any detailed evaluation. And when you need it, you just weigh it and mix it with olefin. That's enough. The reason we use this specific pyridine substituted ketone is in order to avoid chromatography. After the hydrogenation reaction, the reaction mixture was filtered to remove carbon, palladium carbon. And then aqueous hydrochloric acid was added to the filtrate and then separated. This ammonium salt go to the aqueous phase, and separated organic phase was evaporated to give the hydrogenated product in almost quantitative yield. Then the aqueous phase was treated with basic media to regenerate the ketone, which is subjected to solar light driven dimerization reaction again by putting in a plastic bag. So this two-step hydrogenation process is very convenient. The scope of the substrate is similar to that of normal hydrogenation reaction using gaseous dihydrogen, as shown here. Monosubstituted disubstituted works well, but aliphatic trisubstituted olefin doesn't work. Since the diol can be weighed exactly, half hydrogenation of olefin is very easy. You can weigh 1.1 equivalent of diol and then treat it with alkyne in the presence of palladium carbon. You don't have to use Lindlar catalyst. Palladium carbon was enough because the exact amount of hydrogen source can be weighed. Then cis hydrogenation occurs selectively without forming saturated hydrocarbon. We also applied this method to asymmetric hydrogenation reaction using this apparatus developed by Troel. I cannot pronounce his family name, but Troel at Ofs in Denmark, he developed this apparatus. In the left chamber, hydrogen gas was evolved by treatment of this diol with palladium carbon. Then hydrogen gas go to the right chamber where olefin and asymmetric catalyst is contained. And then asymmetric hydrogenation occurs to give this amino ester in good yield with excellent enantiomer selectivity. So this method is applicable to various hydrogenation reactions. So why solar light? Because we initiated this solar light driven reaction since earthquake which hit Japan 10 years ago, 2011. I show you a horrible picture on the next slide. You know, here is a ground level. Here is a seawater level, total black seawater, and it swallowed these cars. It was a terrible view. And as you know, this disaster was followed by another disaster at the nuclear power plant. So these disasters, the impact of these disasters was huge enough to change my research attitude. Up to 2011, my research was more or less driven by curiosity, but then I wanted get my research associated with societal needs like energy issue or environmental issues. That's why I started to tackle these issues, exploitation of solar energy and how to capture carbon dioxide into an organic framework. Here is a simple energy profile. Products have to be more stable than the starting substance. The reaction proceeds from left to right. We use catalysts to lower the height of the mountain to accelerate a reaction or get selectivity. If the height of the mountain leading to R and S isomers are differentiated, then we can get the energy of selectivity. So we are more or less concerned with the height of the mountain. But we cannot change the energy balance. We cannot make the reaction uphill in energy as far as we use thermal reactions. On the other hand, in the case of photoreaction, the starting substance vertically jump up to energetically higher compound by absorption of energy of light. This slide shows you our concept. We irradiate the starting substance. Starting substance absorbs the energy of light to become energetically higher intermediate. Then we carry out our favorite thermal reaction, catalyzed or uncatalyzed, leading to the desired product. At the end of the day, this product can be energetically even higher, which is impossible to carry out as far as you use only thermal reaction. First step is photoreaction. Second step is thermal reaction. This is a first example, and dimerization of this aromatic ketone is energy gaining step. And production of dihydrogen from this diol is thermal reaction, using the stored energy as a driving force. Now, second example, synthesis of window from this amino ketone. Mechanistically, this process consists of 4 steps. First, photocyclization. Second, rhodium catalyzed rearrangement reaction. Third, dehydration reaction. I explain step by step. First, photocyclization reaction of this amino ketone making this 4-membered alcohol. Initially, this ketone was activated by irradiation of light. Activated oxygen pick up this hydrogen to generate a kind of biradical species, which undergoes coupling to make a 4-membered alcohol. This reaction is also not new, has been known for many years. We simply used this reaction to make this 4-membered alcohol. So this is a spectrum of solar light. Solar light contains 5% of UV light, which range from 300 and 400 nanometer in wavelengths. We use this UV light to activate carbonyl oxygen. Now the second step, which is a thermal reaction catalyzed by rhodium hydroxide. When this 4-membered alcohol was treated with rhodium hydroxide, we got this 5-membered alcohol. Initially, this hydroxyl group was deprotonated by rhodium hydroxide, which acted as a kind of base to generate rhodium alkoxide. Then this carbon-carbon single bond in red was cleaved by beta carbon elimination to generate this alkyl rhodium species. Here is an aromatic CH bond, and this rhodium prefers sp2 carbon rather than sp3 carbon. That's why it undergo 1,4 rhodium shift to generate this aryl rhodium species. This is nucleophilic. So it undergoes nucleophilic addition to this carbonyl group intramolecularly to make a fine member ring. Finally, protonation afforded this fine membered alcohol. Now the third step, which is dehydration catalyzed by simple Brensted acid. This tertiary alcohol undergo dehydration upon treatment with hydrochloric acid to generate this indole. So this indole was synthesized from this amino alcohol through 3 steps. First, the photocyclization. Second, rhodium catalyzed rearrangement reaction. Third, dehydration reaction. Now the third example, which incorporates carbon dioxide into an organic molecule by utilization of solar light. It consists of 2 steps. First, photocyclization, like the previous case. Second, CO2 incorporation reaction. I explain step by step again. First step is photocyclization reaction. The mechanism is same with that of the previous example. This is reaction profile. Starting substance decrease, product increase. The reaction occurs even on a cloudy day. This red line is on a cloudy day. This purple line on a cloudy day. Of course, the reaction was slower on a cloudy day, but it happens. And this dotted line corresponds to 35% conversion. On a sunny day, it needs 0.6 kilowatt-hour square meter irradiation of solar light in order to reach this 35% conversion. But on a cloudy day, even less amount of solar light was enough to reach the same conversion. 0.5 kilowatt-hour per square meter was enough. Why? Because light of shorter wavelengths penetrate cloud more easily than longer light. So on a cloudy day, we don't see visible light, but UV light reach at the surface of this planet, even on a cloudy day, go through cloud very easy. Now the second step, which is a thermal reaction catalyzed by cesium carbonate. Initially, this hydroxyl group was deprotonated by base. Then this alkoxide capture carbon dioxide as a carbonate anion. Then this anionic oxygen undergo nucleophilic substitution reaction here to open the 4-member ring to make amide. Then protonation afforded this cyclic carbonate in good yield. Exactly identical conditions were applied to this alcohol having a 5-member ring instead of 4-member ring, and nothing happened. So the contrast between this 4-member ring alcohol and 5-member ring alcohol clearly suggests that the release of the ring strain of the 4-member ring is the key for the capture of carbon dioxide into this skeleton. This is a substrate scope of this carbon dioxide capturing reaction. So this is a schematic slide. So this starting substance, amino ketone, absorbs the energy of sunlight to become energetically higher intermediate. Then the energy stored in this molecule in a form of strain was released to capture carbon dioxide into this skeleton. Yes, solar energy was used to capture carbon dioxide, but in the previous case, the formal oxidation state of carbon dioxide doesn't change. I mean, this +4 to +4. So next, we wanted to capture carbon dioxide by making a carbon-carbon bond between carbon dioxide. Now, the fourth example, carboxylation reaction into this molecule making this carboxylic acid. This ketone was simply irradiated with solar light under the atmospheric pressure of carbon dioxide. Then we got this carboxylic acid in 72% view. Carbon dioxide was fixed on this methyl carbon. Yeah, this reaction was very simple. Here is a flask containing DMSO solution of this aromatic ketone. Here is a balloon containing CO2. This apparatus was simply put on the rooftop of a chemistry building, and after 7 hours, we got carboxylic acid. Here is another concept we are heavily concerned with in developing a new reaction. That's substrate availability, which was clearly mentioned by Sharpless at his Nobel lecture. The starting substance of any synthetically useful reaction has to be easily available. Otherwise, it can't be synthetically useful. Everybody knows this concept, but not everybody practices it, including myself. But now I'm very much concerned with this concept of substrate availability. And the starting substance in this reaction is very much easily available by textbook reaction, Friedel-Crafts acylation reaction. Simply treatment of this acyl chloride in benzene with aluminum chloride was enough to get this starting substance. Then this was irradiated with solar light under atmospheric pressure of carbon dioxide, and we got this carboxylic acid. Initially, this carbonyl group was activated by photon. Activated oxygen pick up this hydrogen to generate a kind of biradical species. Here is a benzene ring in between. Therefore, it immediately generates the quinodimethane, which has a closed shell structure. There are two stereoisomers possibly generated from this biradical species, one having an inward hydroxy group, the other one having outward oriented hydroxy group. The one at the top undergo 1,5 hydrogen proton transfer to revert to the starting substance. Nothing happened. But the one at the bottom undergo 4+2 cycle addition, deals other type cycle addition reaction with carbon dioxide to generate this hemiacetal, which undergo ring opening to give this carboxylic acid. From here to quinodimethane, it has been long known, nothing new. And what we found for the first time was this quinodimethane undergo 4+2 cycle addition with carbon dioxide. I think this is the first example of Diels-Alder type cycle addition reaction in which carbon dioxide participated in as a dienophile. Yeah, carbon dioxide is so thermodynamically stable, so difficult to participate in 4+2 cycle addition as a dienophile. So in this transformation, formal oxidation state of carbon dioxide change from +4 to +3. So CO2 was reduced by solar light. So this is a calculated energy profile of 4+2 cycle addition reaction. We could locate the transition state whose energy is only 17 kilocalorie per mole, which is easily surmountable at room temperature. But at the transition state, the distance here and the distance here are pretty different. So I would say this transition state is concerted but asynchronous transition state. This is the energy profile of the whole reaction. Starting substance, this ketone and carbon dioxide was irradiated with light to become energetically higher intermediate. Then a thermal reaction, 4+2 cycle addition follows, leading to the product. At the end of the day, this carboxylic acid is energetically even higher than the starting substance. So first step is photoreaction, second step is thermal reaction. This is a conceptual slide I showed you previously. So pretty well matching with the energy profile. As you know, photosynthesis also consists of two steps, light reaction and dark reaction. In the first step of light reaction, energy of solar light is stored in these molecules. In the second step of dark reaction, the energy stored in these molecules are utilized to reduce carbon dioxide, making a sugar molecule. So our concept mimics the concept of photosynthesis. So in this reaction, we don't use any base or metal, simply UV light or solar light was enough. The product produced carboxylic acid is useful intermediate. For example, by treatment of hydrogen, we got this seven-membered ring hetero cycle. This is a core structure of various tranquilizer, drug of mental disorder. So we next applied our reaction to the synthesis of this tofisopam, which is a drug sold in European countries and Japan. This is a starting substance we need. And again, this is very easily available by Friedel-Crafts acylation reaction between these two molecules. Both of these compounds are plant origin and cheap, easily available. Now we got this ketone, and we applied our carboxylation reaction to get this carboxylic acid. Then treatment with hydrogen gave this seven-membering heterocycle. The following chlorination and methylation gave rise to tofisopam in 5 steps, 35 total yield. Now, fifth example. Again, this dimerization of benzophenone has been long known. It is contained in a volume of organic synthesis. We used this cyclic benzophenone instead of simple benzophenone for the convenience of experimental procedure. When we use this sunlight collector, it needs a few days to complete dimerization. But if we use LED UV lamp, it will be finished in 1 hour. This is energetically higher than the starting substance by 20 kilocalorie per mole. In other words, this stores the energy of light of 20 kilocalorie per mole as a chemical form, I mean, in the form of strain. The strain is obvious in this structure. The carbon-carbon single bond in red here is a little bit elongated if compared with similar non-strained alcohol. And also, these two benzene rings are bent back to avoid steric repulsion between these two bulky groups. So 20 kilocalorie per mole of energy is stored in this molecule in the form of steric strain. And this was easily released upon treatment with base, for example, tertiary butoxide. It shows clear evidence of ketyl radical. This acts as a reductant. So we used this for reduction of nickel 2 complex to nickel 0 complex. This procedure is for preparation of nickel COD complex yellow powder. This is often used for making other nickel complexes. In literature, diver or sodium are used as a reductant of nickel 2. In the case of diver, the source of electron for reduction that contained in 1s orbital of hydrido. In the case of sodium, electron contained in 3s orbital is the source of electron for reduction. But in this case, the source of electron for reduction is those contained in a sigma bond. This is stable toward water and oxygen. It can be stored on the shelf for months. These diver or sodium need skill to handle and explosive, unstable toward water and oxygen. So this, organo reductant is much better than these hazardous reductant. I think this method will become the standard method to prepare nickel COD complex in the future. The key point of this preparation of nickel COD complex is, this ketyl radical become a source of single electron transfer toward nickel 2 complex. This property was used in this cross-coupling reaction. This reaction itself was reported by Daniel Wex. He used manganese as a reductant of nickel catalyst. But we demonstrate that this diol can replace this manganese in this cross-coupling reaction between bromobenzene and alkyl iodide. We also demonstrate that this diol can be used as a reductant of platinum 2 species to platinum 0. Now, 6th example, carboxylation of benzophenone. This reaction was originally found by Yanagida, but the result was not clear enough. So we investigated this carboxylation reaction, and we found that this diol undergo carboxylation reaction in the presence of base. Initially, one hydroxy group was deprotonated, And then this alkoxide undergo a kind of beta carbon elimination to create a carbon-carbon bond here, located in the center of this diode, to generate an ionic species which undergo nucleophilic addition to carbon dioxide to give rise to carboxylic acid. This carboxylic acid was esterified by treatment with methanol to give this methyl ester. And then this was treated with bromobenzene in the presence of palladium catalyst. And we got this ester in 90% yield. Yes, this methoxycarbonyl group was transferred onto this bromobenzene. Here is a proposed mechanism. Initially, this hydroxyl group was deprotonated to generate alkoxide. On the other hand, the bromobenzene undergo oxidative addition to palladium to generate palladium-2 species. Then this bromide anion was replaced by this oxide to generate this palladium-2 species. Then beta carbon elimination occurs to cleave this CC bond here. Now, methoxycarbonyl group is on the palladium. This undergo reductive elimination to give rise to the ester. That's what we assume for this reaction. Now, the last example. Carboxylation reaction of hydrocarbon, allylic olefin. When cyclohexene was irradiated with UV light in the presence of base and carbon dioxide, we got this carboxylic acid. Turnover number in terms of this ketone was 11. Turnout TON in terms of kappa was 53. Not fancy, but still it demonstrates that the catalytic cycle may work out. This is a mechanism we propose. A bit complicated, but I explain one by one. The yellow cycle on the left corresponds to the light reaction in the photosynthesis. The left cycle in blue corresponds to the dark reaction in photosynthesis. Initially, I explained light reaction. When cyclohexene and this ketone was irradiated with UV light, we got this tertiary alcohol. This is energetically higher than the starting substance. In other words, this molecule stores the energy of light of 30 kilocalorie per mole as a steric strain. Initially, this carbonyl group was activated. Activated oxygen pick up this hydrogen to generate two radical species, which are located in close proximity. Therefore, they undergo cross-coupling to give rise this alcohol. Now, second step, dark, which corresponds to dark reaction. This strained alcohol was treated with carbon dioxide in the presence of kappa catalyst and base, and we got this carboxylic acid. Initially, hydroxyl group was deprotonated by base in the presence of kappa chloride to generate kappa alkoxide. Then, beta carbon elimination follows to generate aryl kappa species, which undergo nucleophilic addition to carbon dioxide to generate this carboxylic acid. Again, initially, carbonyl group is activated by photon. Activated oxygen pick up this hydrogen to generate two radical species which couple to give this strained alcohol. This is energetically high. and then energy stored in this molecule was released by beta carbon elimination to generate allyl kappa species, which undergo nucleophilic addition onto carbon dioxide to generate carboxylic acid. So in this process, allyl kappa was generated, but it's impossible to deprotonate allylic hydrogen with alkoxide base because this is much more acidic. But we did it by making a detour with the aid of light and this ketone. We once prepare this strained tertiary alcohol, then stored energy in this molecule was released by beta carbon elimination to generate allyl kappa species. So this is a tricky method to deprotonate allylic hydrogen. So I showed you 7 examples which fit in this conceptual slide. I hope you were convinced that this concept may work if the reaction is well organized, designed. The chemistry I talked about today were carried out by these people. And this is Dr. Ishida, associate professor in my group. This is Dr. Masuda, who is now at Hokkaido University for Sawamura's group. I very much grateful for these people. So thank you very much for your attention.
Thank you, Professor Murakami, for this interesting lecture. You showed us some nice examples of chemical reactions using solar and UV light in the broader context of societal needs driven science. Okay, I see some hands are raised, and there are also some questions in the Q&A. Let me first give the word to Shubik. Yeah. I think you were first raising your hand.
Masahiro, what a great start of this symposium. Thank you very much for this inspiring chemistry. I also welcome Bukhard, so I now see Bukhard is there as well. So my question is, so of course solar energy, if we can, let's say, harvest for organic synthesis, nothing can be better than that. But how is the scale of things? So when or how big scale do you think you can go with this solar, directly harvesting solar energy?
So far, we have been successful in scaling up to a few grams.
Okay.
But not more.
Do you think the flow photocatalysis it's becoming quite popular? I mean, Bukhard is here, so Bukhard is one of the leading experts in this field. So my question is, do you think also flow solar photocatalysis, do you think it can be another option for that?
Yeah, if it is possible. I mean, flow photoreactor is known, but I don't know any apparatus for solar light driven photo flow reactor. That would be fantastic.
Okay, thank you, Masahiro. Yeah.
Welcome.
Thank you. Burkhard, you have a question?
Yes, definitely. Thank you, Professor Murakami. Very nice. As you know, I follow this work very closely and always admire the achievements. Very, very nice. The carboxylation, I think, is a passion we both share, no? To put CO2 into CH bonds. I have a question to the chemistry you explained to us on your slide 65. You showed us the mechanism of the activation of the allylic CH bond. And you do this by a trick. So you make a triplet. So the oxygen-centered radical, then to transfer the radical to make the kind of alpha alkoxy radical, and then the two radicals combine. I have two questions to this. The one thing is on the carbonyl group, this must be limited to benzophenones and acetophenones, because otherwise the triplet is not, there's not enough triplet. I think this is correct, no? So you can only use, yeah. And
not acetophenone, but benzophenone type, two aromatic groups.
Yes, you need the aromatic group, yeah. And then I was wondering, because you proposed the radical-radical combination on there, and the allylic radical, that is, to me, a more electron-rich radical, and the alpha alkoxy is definitely an electron-rich radical. So to me, it would not be so likely that they combine. Do you have experimental evidence for these radical-radical combination? Do you also see other cross-coupling? Do you see diols or the allylic radical dimerizing in competition? Do you see other products of the radical intermediates?
Oops. No.
You want to share your screen again, or?
Yes. But,
okay, because we don't see your slides on this moment.
Okay, okay. Now I can see.
Yeah, now we can see.
Yeah.
You are asking this step.
Yeah, this step is a specific one because here you use a special ketone. But in principle, yes, the two radicals that you have here these are two relative persistent radicals, but the polarity of the radical-radical coupling to me looks not perfect. So you also see diol formation, so that the blue radical is dimerizing, or the allyl coupling, so that you do have a homocoupling of the radicals, or is it exclusively cross-coupling?
Yeah, we see dimerization also.
All right. Mm-hmm.
But as I have mentioned, you know, these two species are located in close proximity because it is generated by hydrogen abstraction by this oxygen. So they are closely located and easy to couple. That's our explanation.
Right. Okay. Mm-hmm. So then this concept should work for all CH bonds having the same stability. So
yes, allylic one is deprotonated.
Yeah. So it also then works for benzylic or similar CH bonds.
That's right.
Right. Mm-hmm. Thank you very much. Thank you.
And we also reported carboxylation reaction of cyclohexane hydrocarbon, saturated hydrocarbon. But in that case, photocatalyst is needed, other than this ketone.
Yeah, I know this example. It's I think this is a fantastic result. This is something where we all would like to go, to have an efficient method to carboxylate hydrocarbons directly. But if I remember correctly, the yield, your reported yield, was not very high.
No.
And it was with a copper catalyst, if I can recall as well.
Yes, and the nickel.
But certainly it was I'd say, one of the most inspiring reaction.
Thank you.
Okay, I see no more hands being raised for urgent questions. I see there are 5 more questions in the Q&A session typed, but unfortunately, due to time restrictions, I think we have to move on to the next talk, but I suggest that Professor Murakami can type the answers still in the Q&A session to as much as possible give a good answer to these questions that are raised.
Sure.
Okay, good. So thank you once more for this wonderful, interesting lecture. And then yes, and then I give the word to Shubik to introduce the next speaker for today. Thank you.
Thank you.
Thank you, Peggy. Thank you, Professor Murakami. Nothing can be better started the symposium. The chemistry, the inspiring chemistry that you have shown us, it actually shows how we are going to deal in the next 3 days. So thank you very much for the startup, for the kick of this meeting. So now our second speaker is Professor Jerome Wasser from EPFL Switzerland. So Professor Wasser received his PhD degree from ETH Zurich in Switzerland in 2006. And he worked with Professor Eric Carrera, everyone knows him. And after his PhD, he moved to the Stanford University to achieve postdoctoral experience from the research group of Professor Barry Trost, a very well-known figure in organic synthesis. In 2007, he came back to the Europe and joined as an assistant professor at EPFL in Switzerland. In 2014, he was promoted to the associate professor position, and since 2019, he is the full professor at EPFL. It's quite obvious that he has won numerous awards and many prestigious research grants. So I'm going to take the name, some of the names. So he has won the ERC Consolidated Grant in 2017. He has received the Springer Heterocyclic Chemistry Award in 2016, Werner Prize in 2014, ERC Starting Grant in 2013, and Silver Medal of the European Young Chemist Award from UChemS in 2012. With this information, I would like to invite Professor Jerome Wasser, and the screen is yours, Jerome. We are very much looking forward.
Okay, thank you, Shubik, for this very nice introduction. I would like to thank you and Professor Kuhl for the invitation. I hope the screen sharing is working fine because I have some weird thing on my own screen.
Oh, we can see your slide.
Okay, perfect. Yeah, so today I wanted to make my talk on the photomediated reaction using high energy compound, a little bit like we saw with Murakami, Professor Murakami. We like also in my group to use this compound where we store a little bit of energy. And for a short outline, I will start in the first part with hypervalent iodine bond, and I will describe 2 projects, in fact, how we go from carboxylic acid to alkyne, and then from alcohol to alkynes. And then I will move to the activation of strain rings. But let me maybe start a little bit from an overview of what we are doing in my group. So my group is interested by developing new disconnections. We are mostly curiosity driven, and we try to develop new reactivity based on high energy compound. The first category of compound are hypervalent iodine reagent, where we use especially the cyclic hypervalent iodine reagent to make an umpolung of the reactivity of standard functional group in synthetic chemistry. The second one is based on the use of ring strained. We started early on by doubly activated rings, and more recently, we moved to single activated rings. And we have now some more applied projects, we more on smart tethering for the functionalization of alkenes. And finally, we have a strong interest in the functionalization of more complex compounds like peptide and protein. And you may ask, where in this picture come the photocatalysis? It came as the tool that we are using to functionalize all these compounds. So over the years, we have developed several metal catalyzed methods, organocatalyzed methods, and photocatalyzed methods for the use of this great reactivity given by hypervalent ion bond on the strain rings. So let's start now with the hypervalent ion bond. And before I move to the Photoredox specific project, I wanted to tell you how we entered this field and how we decided to use this reagent that a few years ago were still pretty exotic compound, and now they are used pretty broadly by the community. we start, in fact, by wanting to do something that is tough to do by the textbook. So in the textbook, we all learn that we can make this acetylide anion, and they are great to transfer to electrophile. But what happens if you want to make the reverse disconnection? So you want to make an electrophilic alkyne to work with nucleophile. We may think that the most obvious electrophile in synthetic chemistry is the alkyl iodide. But then if you compare the electronegativity of the CSP center and the iodine, they are very similar, and these compounds are very low reactivity. There is some metal that can activate them, but very often they are not broadly applicable. So we looked at the literature at that time, and that's where I become aware of the hypervalent iodine reagent. So these compounds are really fascinating because they break the octet rules. So you have this arrangement of 3 atoms on 4 electrons, making the hypervalent bond. And you have 4 electrons, 2 of them of non-bonding, only 2 bonding. So you could roughly estimate that the bond order is 0.5, and these bonds are therefore very reactive. Naturally, we didn't invent this compound. There was a broad literature already in the past. They were discovered by Behringer in the 60s, 70s. And then the group of Stang, Ochiai, and Zdankid made beautiful work on this compound in the 80s and 90s. But then they were a little bit forgotten since then. And we are thinking that's really a great reactivity to develop new chemistry with alkyne. And the very first transformation we tried was to make the alkyne transfer to an indole. Indole is one of the most important heterocycles in nature and in medicinal chemistry, and introducing an alkyne directly on it was not known at the time. And we tried a lot of different catalysts and conditions with the reported alkynyl iodonium salt, but we were never able to reach the desired product. So we realized that these compounds are too unstable in presence of the metal, and they will just decompose rapidly. So we were at the look for more stable compound, and we get interesting in the cyclic derivative. So this was in 2008. So a few years after Antonio Toni, my colleague in ETH Zurich, has introduced the Toni reagent for trifluoromethylation and demonstrate the high stability of this compound. The alkynyl reagent were known even before, discovered by Ochiai, and then Zdankid exploited a little bit more and developed their synthesis, but they were never used in synthetic chemistry. So we were very pleased to see at that time that we could develop the gold catalyzed method for the functionalization of indole using the cyclic reagent that we call ethinyl benziodoxolones, or shorter EBX reagent. And what maybe was the luck factor in there is that these reagents are not limited only to one type of reaction. They are broadly applicable, and they are also easy to synthesize. So the Zdankid protocol works well on large scale, but it was still 2 linear steps and 3 total steps. So recently, we improved a little bit this protocol, and we were able to develop a single-step procedure from commercially available compounds. So you can, in 1 step, 2 pot, get 36 grams of the compound, starting directly from the free alkyne and 2-iodobenzoic acid. And this compound is now also commercially available. It was applicable in many transformations. In our lab, we started with metal catalysis. We also exploited for the functionalization of alkene, the direct functionalization of nucleophile, the functionalization of carbene, and that's what will be the topic today. We exploit the reactivity of this alkyne in photoredox chemistry. Other groups were also interested to use this type of reagent, and nowadays many different transformations have been reported, and these continue to extend. So these reagents are really very successful, and I think they are successful because they combine high reactivity with a higher stability compared to the non-cyclic alkynyl iodonium salt. So now to the topic of today, to the interface with photoredox chemistry. So thanks to Professor Murakami, I don't have a lot to introduce, but I just wanted to go again to the concept of activating compound with light. So from a simple organic chemist like myself, is an interesting concept because you can just get an activated triplet compound that is at the same time a stronger reductant and a stronger oxidant. And then you can access the 2 possible cycles of a photoredox chemistry that are now very well established, I think. As an organic chemist, I always have a little bit to struggle to call the cycle with the name oxidative quenching, where the substrate is reduced, and the reductive quenching, where the substrate is oxidized. And if you look on EBX reagent, what would be the interface with this type of catalytic cycle? So EBX reagents are excellent radical trap, especially for nucleophilic radicals. And there will be many ways to combine them with Photoredox catalytic cycle. So the first project that I will present to you was started by Frank and continued by Mario. And I have to say, it's really Frank that initiated the Photoredox chemistry in my group because he really believed that it will work and started this project nearly on his own. And the idea of Frank was to convert carboxylic acid into alkyne. So just before we started this research, Professor Li in Shanghai developed a very interesting transformation where he demonstrated that under classical oxidative condition, you can generate a radical from carboxylic acid, and then you can alkylate the formed radical in very high efficiency using the EBX reagent. So this was a very nice protocol. It was cheap, selective, and it has quite a broad scope. But there was still this problem of the classical, very strong oxidative condition to generate the radical. A few years later, Yun Chen developed the first Photoredox-based method for the alkylation of carboxylic acid. But for this method, he had to make an activated ester, and then the ester was reduced by the photocatalyst, and the radical was intercepted by an alkynyl sulfone to generate the product. And over the year, we have seen that the alkynyl sulfone are better trapped under reductive condition, whereas the EBX are better trapped under the oxidative condition. So we wondered at that time, can we develop a really efficient reaction where we can use directly the broadly available carboxylic acid and then transform it to the alkyne under mild photoredox condition without the need of pre-activation. So the working system for this compound is demonstrated now on proline, and we could naturally use the already extensive investigation of other researchers like Dave Macmillan. So it was known that if you activate a photocatalyst, it will become a stronger oxidant able to decarboxylate proline in presence of a base. The formed radical can then react with the EBX reagent, and this has been demonstrated by Li to be an efficient process. And after cleavage of the carbon iodine bond, we'll get iodosyl radical that is better shown, in fact, in the resonance structure with the oxygen-centered radical. And now the question for this project to work would be, will it be possible to close the catalytic cycle and transfer the electron back from the metal to the organic radical? And at this point, we will have closed the catalytic cycle and get back to the starting catalyst. There was a few indications of what we would need for this process to be successful. So first, the reduction potential for the carboxylic acid in proline was known, is roughly around +1 volt. And then the oxidation potential of the radical was not known, and it's very difficult to get it. So we could calculate it to be around 0.25 volt. It's lower than the benzoyl radical because of the stabilization by resonance energy. So with this number in mind, what is nice naturally in photoredox chemistry that we know the thermodynamics. Naturally, the thermodynamics is not everything, and the kinetic is very important, but still it can allow you to tell if a process is possible or not. So in the red line, you have the oxidation potential in the excited state, and in the blue line is the reduction potential in the ground state. And you see basically that all the catalysts below this bar are not strong enough to decarboxylate proline. And in fact, if you do the reaction with this catalyst, you will just get no conversion at all. All the catalysts on the top, in theory, should have been able to do the reaction because their reduction power is efficient enough for all of them. But in reality, only one of them works. And this is probably one of the most successful iridium photocatalysts in organic chemistry nowadays that has been used a lot by the Macmillan group. And it gives us a very efficient transformation in this case. So the scope of this reaction was very good. So we were able to transform many amino acid into the alkyne, also oxo acid, and with more moderate simple carboxylic acid. And I have to say that this idea was in the air at the time, because at the same time we published our work, Professor Xiao published a very similar work back to back with our work. So once we have made this proof of concept with carboxylic acid, we wanted naturally to extend this concept to other possible transformation. And one first idea we had was to use fragmentation reaction that allow you to get more functionalized product. And here we were inspired by the seminal work of Zamir Sard that demonstrate that if you generate an immunyl radical on a strain ring, you will get the fragmentation reaction, and you can intercept the formed radical with a radical trap, like in the Giese reaction in this case. Concerning the use of Photoredox catalyst, there was two project publications that came shortly before we published our work. So the first one by Professor Xiao was using a reductive approach, and the second one by Professor Leonori was using an oxidative approach from a carboxylate followed by an acetone fragmentation. And we were especially interested by the second approach because it would be compatible with our reaction condition. In the work of Professor Leonori, only CX bond formation was formed, and we didn't add an example of CC bond formation. So we thought it was still some interesting expansion to do there. Maybe a comment on the synthesis of the oxime that you need to make this product. So you need the hydroxylamine, and this hydroxylamine is commercially available, but very expensive. And this synthesis was published only in a Chinese patent, available in Chinese only. So we improved the synthesis and developed a larger scale procedure. And it is now very easy, in fact, to condense this hydroxylamine with the ketone. We then try first the condition developed by Professor Leonori using the acridinium guy. So the reaction worked, but it was sluggish, give low yield on several side products in this transformation. So we decided to investigate other type of photocatalysts. And again, we looked a little bit at the thermodynamic of the process. So here is the photocatalyst we have used previously, the iridium biased photocatalyst. And here is the Fukusumi dye. And the question is, where is our starting material now? So the starting material is around plus 1.5 volts. So we see the iridium catalyst is a little bit weak. The Fukusumi dye is really a little bit too strong. So we are looking for another organocatalyst that would be able to perform this transformation. We were especially interested by the carbazole-based dye developed by Zheng. And at that time, they were still pretty new. Now they are really used extensively. They are still a little bit weak, but nevertheless, the reaction was much cleaner than with the Fukusumi dye, even if we were not able to reach full conversion. So we wondered how we could increase the oxidation power of this photocatalyst. And it's not so difficult. You just need to make the carbazole ring a little bit more electron deficient. And we introduce a chloride on the carbazole. This compound is now a slightly stronger oxidant. And indeed, when you use this photocatalyst, you can get full conversion on the good yield in the fragmentation reaction. So this catalyst was known before, but it has not been used yet for photoredox catalyst. It is very easy to prepare. We use sodium hydride in THF to deprotonate the carbazole and make the tetra aromatic substitution reaction. And it can have a nice surface as calculated by our colleague, Professor Cormanbuff. And what was a little bit a small surprise, in fact, this compound by the introduction of chloride is not anymore completely symmetrical, but you begin to have halogen-halogen interaction so that one of the ring is tilting against the other one. And we could show, in fact, that there was indeed observed in the X-ray structure of the compound. So you have the two carbazole rings that are closer to each other. And my student in my lab like to give nickname to the catalyst. And I decided to call this one the dragoon catalyst. So you may see the similitude between the dragoon and the carbazole ring in this catalyst. And it is a very good catalyst if you have some need of something that is slightly stronger oxidant than the 4-CZ-IPN catalyst. So the reaction itself works very well. So here is just a short example of the scope we can do. So we can make the alkynyl nitrile in good yield with different substituents on the backbone. And these are interesting starting material, for example, for the synthesis of pyridine. But for us, it was really an important project because it allowed us to better understand this class of organocatalyst or carbazole photocatalyst. And they will be very important also in other projects in the group. And this next project I want to present to you was to extend this work to peptide. And as I said, we have a strong interest now in our group to move to peptide and maybe one day proteins functionalization. I think is a very interesting interface for organic chemists for the future work. And our original protocol was not working at all already if you just introduce a protected glycine. So it was really a little bit limited in this respect. And Marion could finally overcome this limitation by moving to the CZ-IPN, but especially by moving to RU-LiBX reagent. And in fact, we discovered that these RU-LiBX reagents are much better radical trap than the silyl derived reagent, and this higher efficiency allow you also to intercept this radical. So it's an important point if you want to use the IBX reagent to functionalize radical, these RU-LiBX are really the way to go. So this chemistry is working very well with different reagents. So you can transfer functional group like aldehyde, azide, or alkyne. So that allow you for further diversification of the compound. And you can also functionalize different dipeptides. So it's important you are not limited to proline. You also go to alanine, phenylalanine, or you can derive the peptide on the other side. So naturally, that motivated us to move to more complex peptide. And we could modify a lot of tetrapeptides. So you need to use a little bit more reagent, and the catalyst loading is more on the 20% stage than 5% stage, but it's still working very well. And we first check the compatibility to different amino acids, and many nucleophilic amino acids are working well. Lysine starts to be an issue, but lysine is usually protonated. So if you are a little bit careful with the reaction condition, that can be still okay. Limitations are a little bit tyrosine, where you needed to change to a less oxiding catalyst again. And tryptophan is still a no-go for this reaction. The tryptophan will be more efficient quencher than the carboxylic final terminus. What is very encouraging, on the other hand, is that the carboxylic acid side chain of aspargic acid or glutamic acid are not reacting under this condition because they are more difficult to oxidize than the C-terminus. So this is a very nice method to allow you to distinguish, in fact, the C-terminus carboxylic acid from the side chain carboxylic acid. If you have a cysteine, there is something different happening because we demonstrate that the IBX reagent is reacting very fast with the cysteine in absence of any catalyst. So we will first alkylate the cysteine and then functionalize the C-terminus. We are then interested to see if other type of terminus would also react under this reaction condition. And we are very pleased to see it is the case. So you can tolerate a lot of amino acid at the C-terminus. The limitation are again tyrosine and tryptophan that just doesn't work well because they are too easy to oxidize. We then extended a little bit the size of the peptide, and we see casomorphine was also giving you a moderate yield. And now you don't see any peptides that are larger than, say, 6, 7, or 10 amino acids. And this is a current limitation of our methodology. As soon as we have a very long peptide chain, we seem to lose our electrons somewhere. So we are not able to decarboxylate selectively anymore. And we just recovered a lot of starting material or decomposition. And there is still, I think, a limitation of this type of oxidative photochemistry on biomolecules. So the Macmillan group has a few examples of larger peptide and protein working, but there is still no good solution, at least in our lab, to move to the larger scale of molecules. What we could do is change a little bit the transformation. So we have now developed the alkylation, and we wondered if we could transfer other functional group using other reagent, especially the cyanide. The cyanide is a very interesting functional group to introduce also on the C-terminus of peptide. And the cyano reagent was already developed and synthesized by Dunkin. So we are thinking it will be also possible to introduce the cyanide into the C-terminus. Under the exactly same condition, the reaction was encouraging. So you get the desired product, but you get a lot of hydroxy product and anhydride formations. So this hydroxy product was interesting in the sense that we didn't have observed it before. We could shut down the side reaction just by some technical improvement, diminish the amount of base, moving to THF, what is kind of a surprising solvent for this type of reaction because it's a solvent that is very prone for CH abstraction, but it was still the best solvent, and using molecular sieve to remove all traces of water. It's also interesting that we could demonstrate by D2O incorporation that this hydroxy group is coming from water or not from oxygen. So that was a hint for us that the mechanism of the two reactions may be slightly different. So we turned back to see if our original working model for this transformation was correct, and we investigate the mechanism of the transformation. So just a few images of the scope. So the cyanide can be transferred to many different amino acids, is working pretty well, also for oxalic acid. But the key difference that also point on different mechanism is that aliphatic acid are not working at all into this transformation. So a first obvious transformation for the mechanism was to see if we can intercept a radical intermediate or see an intermediate. And we see that with a radical clock, with this cyclopropane derivative, we see a fast ring opening to get the ring open product in moderate yield. With the amino acid derivative, we also see the ring opening product, but we isolate an aldehyde, and we think that the aldehyde is coming from the enamide after hydrolysis upon workup. For the cyano compound, we are not able to isolate this product, but we are still able to stop the reaction in presence of tempo and observe the tempo adduct by mass spectrometry. Further experiments that were suggested, in fact, by the reviewer, and that we are grateful from the reviewer, that were important questions to be answered. So the first one is there really no interaction between the activated photocatalyst and the IBX reagent? Because that's naturally a very reactive reagent. And we checked that carefully with Stern-Follmer studies, and we see that the fluorescence of the iridium catalyst is rapidly quenched by the cesium carboxylate, showing you that you have an electron transfer, but the fluorescence is not at all quenched by the TIPS-IBX reagent. So showing that the step involving reaction of the activated photocatalyst with the reagent is not very probable. Another question that can be asked is, do we have a radical chain process or not? That is, in my opinion, very difficult to exclude. So we checked the quantum yield of the reaction and we found it to be 79%. I found it a little bit high, but it's still not an indication that we have a radical chain. So to better understand the alkylation step, once we assume we form the radical, we turn then to computational chemistry. And these calculations were done by Dr. Matt Wodrich. And we first investigate a reaction of the radical at the alpha position. And what we found, in fact, is a direct concerted transition state. So you never make the full radical addition because the carbon iodine bond is so weak that you will cleave immediately to go to the product. So you get a kind of concerted asynchronous radical addition, say iodine bond cleavage, to get the iodosyl radical. But it's also possible for the radical to add at the beta position. It's even slightly lower energy, or I would say the same energy. In this case, you can locate a radical intermediate. What happens next is a very fast 1-2 shift of the silicon group to get to the product on the iodosyl radical. And what we were wondering is if you could have a second single electron transfer. So if you could oxidize this radical to the iminium. So this is endothermic, and in principle would still be possible. It's not too high in energy. But once you have this radical anion, this is pretty stable. And to dissociate and make the acetylide would be very high in energy. So this looks like not probable. So we don't think that you have oxidation to the iminium in this pathway for alkylation. Now let's look about the seemingly small perturbation to replace the alkyne with a cyanide group and see what would happen under this condition. So I will not insist too much on the first pathway because the first pathway is looking very similar to the one with the alkyne. So we could locate it the same alpha transition state to go to the product. On the other hand, the beta transition state is higher in energy, and they will look to an isonitrile. So isonitrile are pretty stable, and they are difficult, in fact, to isomerize to the cyanide. So we should have observed this isonitrile, but we never observed it. And now, naturally, the question is, what happened with the second single electron transfer? Indeed, the cyanobenzodoxolone is a much stronger oxidant. So this is now able to oxidize the radical to the iminium with a much lower energy cost. And this radical anion can dissociate really easily to give the cyanide. And then recombination is barrierless to get to the product. And now we see that apparently for cyanide, the two single electron transfer process is favored, and we can better understand why water can add onto this iminium, and we observe different side product. Okay, so that's where we are now. We are still trying to develop other reaction of carboxylic acid, but now I wanted to go to a second project that we developed very recently in my lab, and it was the question to go from alcohols to alkynes. So this work was also started quite a long time ago by Frank, but it takes us several years, also with the work of Stephanie and Diana, to make it fully work, also of the context of the NCCR catalysis. So we have developed now the decarboxylation of carboxylic acid. What about the transfer of oxygen to alkyne? So this is a little bit more difficult because you cannot get a direct transformation. So you need to activate your alcohol. And the state of the art in the field was Fu's work, where he introduced this oxalate derivated phthalimide derivative that can be used under the reductive condition. It will just fragment upon generation of CO2, and then you can get the alkyne product. But this is an oxidative quenching, not suitable for EBX, and you really need to introduce a quite large group for activation. And our starting idea was pretty simple. Can we use the simple cesium oxalates that were popularized by Overman and Macmillan to do the similar transformation using EBX reagent? And we are pleased to see that the 4CZ-IPN catalyst is working very well for this transformation using Kessel lamp on the activated cesium oxalate, so we can transfer a broad range of alkyne and alkyl group to get the aliphatic alkyne product. A current limitation of this transformation is that it works only for tertiary radical. If you don't form a tertiary radical, the reaction usually stops in midway, and you just get an alkynyl ester as product. So then we did maybe the control experiment that we should have done in the start of the project is a control experiment we always do. What happens if you do the reaction with irradiation in the absence of the photocatalyst? And in all the projects I did before, we did this control experiment, and we didn't see any formation of the product. So we are pretty confident we will get 0%. And the surprise was that, in fact, in absence of photocatalyst, this reaction is pretty efficient. So we tried to understand why we observed this effect for the first time. And we first wondered, is this reagent not clean? Because these happen in other projects. There is precursor in this, on the synthesis of the reagent, especially this hydroxybenzodioxolone that can be present if you are not careful in 4 or 5%. But this was not a promoter of the reaction. We then carefully analyzed the reaction to see if there was side product formed during the catalytic process. And in fact, if you analyze the reaction mixture, you can see that you have several impurities. So these ketone coming from the hydration redox rearrangement of the EBX reagent, the addition of the oxalate on the ketone, and diene. But not of this impurity was a photocatalyst, so they were not able to promote the reaction. Finally, we came to the conclusion that the reagent itself is photoactive and can be activated by light. And that was surprising because we never observed this type of photoactivation. But what happened in my lab is that when the new students started, they decided to improve a little bit the yield by going to more powerful lamps. And in fact, if you use LED strips of 8 watt, you get no reaction. But the blue Kessel lamp that are much stronger, then you can observe this reaction. So it seems that photoactivation is possible, but you need a very strong activation process. So let's look a little bit more in detail on the photo properties of the phenyl EBX. So the absorbance of phenyl EBX is mostly ranged in the UV range, but you still see that you have in the visible light range quite a strong tailing. If you look at the fluorescence around 300 nanometer, that's the curve you obtain. And now the most interesting is to do the fluorescence excitation experiment. And you see that you have the main band around 360, and then an interesting weak band around 440 nanometer. And this is exactly the irradiation spectrum of your Kessel lamp. So we think that this weak band may be responsible for the photoexcitation of phenyl EBX. And this weak band is absent for the silicon-based reagent. So that's why it is not really photoactive, but the aryl EBX are. It may be a forbidden transition from directly to the triplet, but we didn't do the photophysics experiment yet to be sure about that. So it's maybe too preliminary to tell that. So now that we have discovered this direct photoexcitation, we wondered naturally if it is a general process. So we start to go back to the literature that all the photocatalytic reactions that have been developed using the aryl EBX reagent. So first we check the deoxygenation of alcohol, and indeed it proceeds well with the without photocatalyst, even if the yields are slightly lower. Simple carboxylic acid or their cesium salt can also be decarboxylated to make alkynyl ketone or aliphatic alkynes. We can also use a fragmentation reaction with yields that are very close to the photocatalytic one in absence of any photocatalyst. You can use the reaction of ion chain, so you can take alkynyl boronate. So the reaction also works well without any photocatalyst. And finally, you can make CH alkylation of the reactive bond for tetrahydrofuran, or you can make a deamination reaction recently developed by the Rovis group under oxidative condition for alkylation. You can make now the alkylation work also. And we estimated the oxidation power in the excited state of this reagent. It should be around 0.18 volt. So that makes it a relatively strong oxidant that can have broad application. And it's kind of practical because you don't need to optimize your photocatalyst. Naturally, you pay a cost for that. You need a larger excess of the reagent because mostly one equivalent is used as an oxidant and another equivalent as alkyne transfer reagent. So with that, I would like to switch gear to the second part of my talk and move to the strain rings. So that work has been done by Bastien Muriel and Mingming Wang. So where do we get interested in strain ring? So it is a very long interest we have in my group is to focus on the synthesis of amine substituted rings because they are present in so many bioactive compounds like vinblastine, paloamine, in natural molecules like DNA, and in synthetic compounds like Tamiflu, Lobukavir. Many antiviral compounds have these carbocycles substituted with a nitrogen. And our idea was pretty simple. We wanted to take the smallest of the rings, the cyclopropane and the cyclobutane, and to extend them using the ring strain to get the other rings. That's naturally a very classical approach of cyclopropane ring activation, this push-pull that were popularized a lot by Reisig or even earlier Wenkert. But the use of nitrogen as a pushing group was not so much established. In presence of a catalyst, you can make a formal 1,3 dipoles, and you can then activate to get via cyclization 1 new bond or annulation 2 new bonds. And we first use classical Lewis acid activation to develop this type of chemistry. We are able first to make annulation reaction. We then develop an enantioselective transformation in a dynamic kinetic asymmetric transformation starting from racemic cyclopropane. And later, we develop also a desymmetrization approach to synthesize this compound with high enantioselectivity. But all this chemistry has one common weak point, is that we still have these electron withdrawing groups that are necessary for activation, and very often you don't want them in your product. So we wondered if we could move to a field of donor-only cyclopropanes. So naturally, we are not the only one interested by the activation of these small rings, and there is 2 schools on how you can eventually activate them. The first one is based on transition metal catalyst. The group of Fanyu and Grimaud developed palladium catalysts, and the group of Bauer had a lot of very interesting results using rhodium catalyst. And the second approach is based on substrate activation. The group of Shah, Zheng, and others have used the oxidation of cyclopropyl anilide to develop cycloaddition reaction, and also using photoredox condition. And we see that where photoredox will come back, and under oxidative condition, you generate the radical cation that will have a radical ring opening to generate the radical. And that's an interesting type of reactive intermediate for further functionalization. The first application we made on this concept was for the synthesis of these bicyclohexanes that are very broadly spread in bioactive natural products and also analogs of drugs. And if you look on how they are made, it's usually to make them via cyclopropanation or cycloisomerization reaction. And we wondered if we could develop a new transformation where this type of bicyclo ring will be done by a cycloaddition between an aminocyclopropane and the cyclopropenes, a process that was never reported before. So here is the working model for this transformation. We will use a photocatalytic approach where, according to Zeng, we will oxidize the aminocyclopropane to the radical cation. After ring opening, the radical will add to the cyclopropenes. And there was indication in the literature that the double bond of cyclopropenes is very reactive towards radicals. In fact, Yannick Landé demonstrated in this beautiful work that this was possible. This radical is pretty reactive, but in this case, it can be internally quenched by the iminium, getting back to a radical cation, then can then transfer, get the electron back from the catalyst to close the catalytic cycle. So this transformation works indeed well. So we found different photocatalysts that were working pretty well for this transformation. As the arylamine is pretty easy to oxidize, we tend to prefer the weaker oxidant to avoid side reaction. And especially this DPIPN catalyst was one of the best for this transformation. Just maybe a warning when you synthesize this catalyst. The original protocol in THF has the risk to stop and you transfer only 3 carbazole. And in fact, in the original publication of Zeng, you have still a fluorine left on the catalyst. It was also demonstrated by Kirsten Zeitler that is the case. But if you push the reaction in DMF, you can get the real catalyst that is in fact a weaker oxidant than the fluorosubstituted compound. So here are just a few examples of the scope of this transformation. So the reaction is working well for diester cyclopropane, difluorocyclopropane, and you can also vary the aryl ring, get TMS or hydrogen to work, but the alkyl cyclopropene, so it doesn't work so well. You can also modify the aryl ring, and when we modify the aryl ring on the amine, we are interested to see that you can get higher diastereoselectivity if you have this very bulky aryl ring. So we focus a little bit on this class of substrate because they are very interesting fluorinated amines for medchem. And in this case, we can get very good yield on diastereoselectivity of the difluoroaminocyclopropane product. And we move to the last oxidizing photocatalyst to avoid in situ deprotection of the amine. And in fact, this protecting group is very easy to remove under oxidative condition to get the free amine that you may be more interested as a building block. The second idea we had for the opening of cyclopropane was based on the very well-established Hofmann-Löffler-Freitag reaction. So in the HLF reaction, we will chlorinate or iodinate an NH bond, and then under light irradiation, we will have 1,5-HIT, we will recombine and then make an SN2-like reaction. So this is an old reaction, but it's very popular nowadays with many new exciting work in this field. But what about performing this reaction on cyclopropane? We could, in principle, chlorinate the aminocyclopropane or iodinate it. Under light irradiation, we'll get a photocleavage. You will then get radical ring opening and then recombination to get now a de-electrophile. So you get a complete umpolung of the aminocyclopropane. And if you look in the literature, we are surprised that this reaction was not reported. We found only one precedence from this Netherlands paper written in French, where you have light irradiation of the N-bromo compound, and what they isolated was the aldehyde, probably because this imine is very difficult to isolate, and you just hydrolyze it during the workup. So we make a proof of concept for this reaction. It worked indeed in poor yield because it's difficult to isolate this imine, and you even don't need to irradiate because the bond is so weak that it cleaves even in the dark. We can then isolate the compound as a methoxy compound, as a alpha-acetal, but it's working only for iodine, bromide, and this doesn't work for fluorine, for example. An interesting difference between iodine and bromine is that the iodine reaction is working in the dark, but for the bromine reaction, you need to have visible light to promote the reaction. And we can further activate a little bit the reaction by using acid co-catalyst, and then you get a very good yield of this transformation. And the power of this transformation is that you can get multifunctionalized compound because you can add the first nucleophile to the imine, and then you can make an SN2 substitution to get a second nucleophile on the iodide. And then you can get a broad diversity of compound. We have also preliminary result that if you use a chiral acid catalyst, you can get enantiopure alpha-acetal. And we are now working to further extend this transformation to other type of nucleophilic addition. But in the last 5 minutes, I wanted to come back to this limitation that for us was a serious limitation. You cannot make fluorinated compound. So we tried another approach to make the fluorinated compound by making the NF bond selectively using an approach developed by Cook and coworker. But we were not able to introduce the fluorine because using NFSI, what we obtain, in fact, is the sulfone product. So we wondered if we could make a direct oxidation. So if we could oxidize the amide, we would then get again the radical ring opening. And then there is broad precedence in the literature that you can use a somophilic fluoride reagent to intercept this radical. But an amide is naturally much more difficult to oxidize than the arylamine. In fact, we measure the cyclic voltammetry, and you will need something like 0.17 volt. This is okay. There is photocatalysts that can reach this value. In fact, the idea worked. If we use select fluor as a fluorine giving reagent in a mixture of acetonitrile in water, you can get this compound in pretty good yield using the acridinium dye. What was more surprising for us is that other organocatalysts that should not have worked because they are too weak oxidant are also working well. So something was wrong with our working model. And we finally decided to use benzophenone that was also shown by Professor Murakami. That was a really cheap one. So it's really like orders of magnitude cheaper than the other photocatalyst. So here is a little bit the scope of this transformation. So you can add different nucleophile to the imine, being oxygen nucleophile, sulfur, nitrogen. You can reduce it, and you can add electron-rich aromatic rings. You can often functionalize cyclopropane. A disadvantage is that you get the diastereoisomer, but if you make a reduction, then you don't have the issue of the diastereoisomer. More complex compound can also be opened. And if you have a defluorinated cyclopropane, you get the fluorine incorporated at the same position as the other fluorine. And finally, you can also open up cyclobutane, but not cyclopentylamines that don't work, but cyclobutylamine works very well to get to this product. And the question is a little bit now, how does this working? I have to say this is a working model. We don't have yet experimental proof. But what we know is that the initial idea is to just get an activated photocatalyst that will close the catalytic cycle doesn't work. And we checked, in fact, there is no fluorescent quenching. So what we observe at the end is that select fluor is able, in fact, is quenched by the activated photocatalyst. So we think that we have the activated benzophenone, and that the activated benzophenone is the oxidant. After that, you can transfer the fluoride. And finally, you have the radical aminium that can also close the catalytic cycle. So that's our current hypothesis on how this reaction is working. Okay, with that, I've come to the end of my talk. And I hope I could show you that it's interesting to use the Photoredox catalysis together with hypervalent iodine reagent on strain ring. And we use the picture of the labyrinth. So we break the wall of the synthetic labyrinth to develop new transformation. That's a few pictures of my department at EPFL. So it's a very nice place to live. We have a strong organic chemistry and bioorganic department. And in fact, this year is special because we are hiring new professors. Tenure track assistant professor in catalysis and chemical biologists and full professor in physical analytical chemistry. So if you are interested, don't hesitate to apply. The closing date is on October 15. And to finish, I would like to thank the organizer again to invite me. I would like to thank all my group members that really they are the ones really doing the work and just making suggestions right now. And I have to thank the ERC and especially the NCCR Catalysis for financial support of my research. And I will be very happy to answer all questions you may still have on my chemistry. Thank you.
Yeah, Jerome, thank you very much for a very interesting and inspiring chemistry. Yeah, you started with carboxylic acid and then you take it through to the cyclopropane ring to get some new compounds. Interesting. It was super nice chemistry. And as usual, you know, when the chemistry is super nice, there will be also more questions. So I do have plenty of questions, but I do see in the Q&A section, there are plenty of questions. So first I start reading the question from the Q&A and then I come. So the first question from Abdur Raub Sami Mondol. Professor Wazir, can we do the conversion of carboxylic acid to alkyne by using EDA concept?
So we checked a little bit this idea. We didn't see any complex form between the carboxylate and the EBX reagent. So we didn't see a covalent. So there's two ways you could think of even making a covalent bond, but we didn't observe that. Or we check if you have a stronger UV absorption between carboxylate and the EBX reagent, but we didn't observe any increased UV absorption. So that seems that there is no strong EDA complex between the two. But maybe if you have the right reagent, it could be possible. Yeah.
Along the same line, Jerome, I have one question, very quick. So in your very first topic, you took carboxylic acid, let's say proline, to generate carbon-centered radical, and then you combine with the alkyne from the hypervalent iodine.
Yeah.
Do you think you can also generate carbon-centered radical directly from CH bond? Because what I observed that you are approaching towards there. So first amino acids, then alcohol, then probably it's also in your working group as well. Yes,
I mean, I think we worked a little bit on that, and it's working very well on ethereal CH bond. But there is already now many other researchers. I think there was like 5 simultaneous publications that you can. It's working very well. I would call it on the obvious suspect, like ethereal CH bond and things like that. And I think the next step would be to find good CH abstractor that can make then more challenging bond, like Burkhardt were telling, non-activated CH bond, because now I consider the activated CH bond is a kind of done deal. And in fact, you even don't need a photocatalyst anymore. You just need to irradiate the reagent in presence of this bond, and you get the alkylation good yield. Yeah.
And then along the same line, another quick question. So you have been able to transfer, let's say, alkyne group. But if I think, how about the transfer of alkane group? Do you think it could be more challenging?
You mean alkene or alkane?
Alkene is known.
Yes, it's known. Alkane. So alkane, you have a big issue that if you have these compounds tend to be non-stable. I think I know only one stable hypervalent alkane reagent, that is a cyclopropane one developed by the group of Suero. So there is here a limitation, but naturally what could be interesting is you can generate them in situ. So the late Professor Munitz always has this hypothesis that you generate an hypervalent iodine reagent in situ. So there may be some things, but you cannot use them because they are not batch stable reagent.
Okay, there is a second question in the Q&A from Sabbashachi Manna. Are the processes exclusive to acid where the radicals can be stabilized by the nitrogen at the alpha position to form the iminium radical? What can happen when the simple long chain aliphatic carboxylic acids are engaged? If not successful, then should we have to change our photocatalyst in those cases to make it work? Sorry, it's a very long question.
Yeah, I mean, they are working, but the yield is lower. The tertiary radical are working pretty fine. The secondary radical are also okay. The primary usually doesn't work well. So there maybe we need another photocatalyst, but we couldn't get the same efficiency. So the yield for the amino acid were around 80, 90, and the yield for aliphatic one were like 30, 50. So the protocol of Lee using strong oxidant was giving better yield in this case. Yeah.
Third question from Bartholomew's paper. Great talk, thank you. Question to part 1.2. How crucial is the cesium cation for the oxalate chemistry? How about other cations? And can you form the salt in situ from the acid by adding, for example, cesium fluoride or a related weak base?
Yeah, so there is a cesium effect because the potassium was gave a much lower result. It's not in all the projects like that, but in this project, the cesium was important. And I think it was not our discovery. It was already discovered by Professor Macmillan that the cesium was important. And then considering the anion you put in the cesium is pretty important. We had best result with cesium. So cesium carbonate is fine if you use phenylABX, but the cesium benzoate is a weaker base, and it's better if you have the cellulose-ABX reagent because those tend to be a little bit base sensitive. Cesium fluoride we tend to avoid because those destroy the cellulose-ABX reagent immediately. So we didn't try them with the phenylebaics. They may be okay in this case, but fluoride is sometimes a problem because it tends to add sometimes also to the hypervalent iodine reagents. So it's maybe not the best one.
Another question from Francisco Julia Hernandez. Nice talk, Jerome. Very interesting finding about the photochemical properties of phenyl EBX. I'm quite curious about the photophysical properties of this reagent. Do you have an idea about the lifetime of the excited of this reagent? That would be nice to assess a plausible intermolecular electron transfer. Also, could one use this reagent as a triplet photosensitizer?
Okay, so the first idea, unfortunately, we don't have yet. So my lab is not very well equipped on these. So we didn't make yet the photophysical experiment or the phosphorescence and things like that. So we don't know really how long this excited state of phenyl-EBX is living. We don't know also the radical anion, how long it's living. We know it's quite unstable because you get a lot of diene formation if you don't have something to react with it. On the question as a triplet photosynthesizer, yeah, it could be an interesting idea, but we didn't yet make all this photophysics experiment. Yeah, could be interesting for future work. Yeah.
Very final question from Jabo Rabea from Leibniz Institute of Catalysis, Rostock. Very interesting talk. Thank you. Is there any attempt to follow the proposed radical reaction mechanism by in situ electron paramagnetic resonance? So EPR. He's an EPR expert.
No, we didn't look at it yet. I don't know. I don't know if the radical, honestly, I will some doubt that they will be long-lived enough. Maybe you probably need to trap them with one of these radical trap using EPR, but then it's naturally only an indirect evidence. But we didn't try yet EPR on these intermediates. Yes.
And I think Jabor is very, very nice guy. So I know him since more than 12 years. Yeah, even more. Okay. Is there any further questions from the panel members? Okay, then we are actually on time. So Jerome, I thank you for this very inspiring lecture, very interesting chemistry, and thank you also for answering all the questions from the audience as well as from the panel members.
Okay, thank you again for the invitation.
With this, I thank Professor Masahiro Murakami as well as Professor Jerome Oase for this wonderful startup of this symposium. And now we'll take a short break for 15 minutes and then we'll come back in 15 minutes. But meanwhile, I would like to welcome Professor Burkhard Koenig, Professor Pascal van der Voort, Dr. Suzanne Tobe, and Professor Liang Nian He. Yes, so thank you very much for joining. We are going to come back very soon.
So yes, let's move on with the third talk of today. I hope everybody is logged in again after the short break we have. And it's my pleasure to introduce our next speaker is Peter Sadler. Peter obtained his bachelor, master and PhD degree at the University of Oxford. Subsequently, he was a Medical Research Council Research Fellow at the University of Cambridge and the National Institute for Medical Research. In the period 1973-96, he was lecturer, reader, and professor at Birkbeck College, University of London, and from 96 till 2007, Crum-Brown Chair of Chemistry at the University of Edinburgh. Also director of the Edinburgh Protein Interaction Centre and East Cam Cancer Research UK Medicinal Chemistry Centre. In June 2007, he took up a chair in chemistry at the University of Warwick as head of the department, where he is now professor. From 2010 till 15, he was an ERC advanced investigator. And from 2012 to 2015, visiting professor in chemistry at the University of Hong Kong. Peter is also fellow of the Royal Society of Chemistry, the Royal Society of Edinburgh, and the Royal Society of London. And he's also an honorary fellow of the Chemical Research Society of India, an honorary fellow of the Chinese Chemical Society, and a fellow of the European Academy of Sciences. I hope I did not forget anything. And Peter will give a talk today on photocatalytic and phototherapeutic metal complexes. Please go ahead, Peter.
Thank you, Petty. I'll just try to share my screen.
Yes, we see your screen. We see your slides.
You can
That's
see
fine.
my screen already. So if,
yeah.
if I just put it on full screen. Do you have it on full screen?
Yes.
Okay.
Yes, perfect.
Okay, thanks very much for that very kind introduction and for inviting me to talk to you at this really very exciting conference. For me, photochemistry and photobiology is some of the most difficult research I think we've ever done in our group, but that really makes it perhaps some of the most exciting. The challenges seem to me to be quite enormous, and I'll try to mention some of these as I go along today, particularly as we work on the borderlines of chemistry, biology, medicine, and in some very difficult media, if you like, with cells and tissues and so on. So I'm going to talk about photocatalytic and phototherapeutic metal complexes. Perhaps I should say immediately, I haven't put in an acknowledgement slide to the people who've done all the work, and so I want to say thank you to them right now. There just seem to be too many people these days. I've worked with a lot of very, very good people, both in my own lab and our collaborators, and I really am very grateful to them all. I've tried to acknowledge them in the bottom of slides, in the papers and so on that we've published, and I'll try and mention them as I go along. So that's the only reason there isn't a list of them, because I might miss some out in the list anyway, because there isn't room. So my area of research is concerned with the periodic table. I'm basically a bioinorganic chemist by training, and I look at the periodic table and I say, well, you know, there are some 19 elements that are essential for life, and even then there might be even more than that. You know, is fluorine really essential or not? There's so much that we do not understand about the role of the inorganic elements in natural biology and in medicine. And when you look at the medicines that we come into contact with every day, there's not much chemistry in some of them, right? You go to the drugstore and it says, buy some zinc or buy some copper. And yet nobody would say, buy some carbon. You know, you'd worry about whether it was cyanide or sugar. But with the inorganic elements, they get sort of brushed off and labeled just for the name of the element. But we know with cobalt that, you know, vitamin B12 is the cobalt we need every day. It's a very specific cobalt compound. And I'm not going to go through all of these today, obviously, but it's something that I've reviewed with this is Professor Challen, who was a postdoc in my group in South Africa, who now has our own lectureship at Stellenbosch University. But, you know, when you look at gadolinium, some of you may well be well aware, millions of people now are getting injections of gadolinium compounds as a contrast agent for MRI imaging. And it's not just any old gadolinium compound. You know, it needs to have special ligands around it to make it safe to administer, to make it good as a contrast agent. And platinum, which I'll come back to later now, you know, 50% at least of all chemotherapies for cancer now use a platinum compound. 50%. And again, it's not just any platinum compounds. There has to be specific platinum compounds, specific coordination spheres. Recently, Cinzia Imberti in my lab and I reviewed what is being used in medicine today. And I think we counted some 76 elements being used. And, you know, they're either in therapy or diagnosis. Some of them are radioisotopes. So there's an enormous interest and really a lot more scope for other people working in the area, because there's a lot of chemistry here to cover. So today I'm going to take really three elements, none of which are essential for life as far as we know. There's ruthenium, and I'll talk about photoactive ruthenium complexes that release antimicrobial compounds. I'll talk about platinum complexes, and we know platinum is in the clinic at the moment, but these are platinum compounds that will not kill cancer cells until we activate them with light. So the idea is to make relatively non-toxic platinum complexes that will have few side effects, that will not damage normal tissues until we shine a light on them. And we hope to be able to do that specifically where the tumor cells are, where the cancer is situated. And then finally, iridium, one of the world's rarest metals. Some people say it was brought to Earth in a meteorite in South America. Very interesting element, iridium, well known for a long time. And again, for photodynamic therapy now, and I'll talk about the differences between these types of therapy later. And this thing that is overriding a lot of what I think about these days, can we study the chemistry of these compounds inside real biological cells, inside complicated media? And that is a massive challenge, and I'll show you a little glimpse of how we're trying to do that. So the elements I'm talking about, the oxidation states of the elements I'm talking about today are all related. Ruthenium 2+ has an outer electronic configuration of 4d6. Iridium 3+ has an outer electronic configuration of 5d6, and it's isoelectronic with platinum 4+, 5d6. So something rather special about these low spin d6 configurations. And I'm sorry if I'm sort of saying things to, so I don't know who's in the audience, so forgive me if you know all of coordination chemistry like this already, but there may be some people who may be organic chemists who are not familiar with this, so I'll say it anyway. That this is a very special configuration, relatively inert, not always, so it means that you can use it in drugs and it will not react too quickly. There's a chance of delivering these complexes to the target site that you want to reach and then irradiate it there and activate it. You don't want it to react too quickly, and you don't want it to be destroyed before it gets to the target site. And then the idea of using some kind of radiation, might be visible light, might be UVA even, might be infrared light, of specifically administering that light to a particular part of the body and activating the photoactive compound just in the region where you want to kill the cancer cells, or might be kill microbes if this is antimicrobial. And you want to convert that pro-drug, if you like, into a highly active drug itself that might kill cells, as you'll see, by different mechanisms. You'll see, it might be by release of heat, it might be release of some cytotoxic molecules, it might be production of single oxygen. So, but the light itself, of course, is quite important. And this is kind of just a diagram, really, because the penetration of light depends on the wavelength. If it's a short wavelength, it's like UVA, and it's not going to penetrate more than a millimeter or two. Blue is a bit better, green's a bit better, all the way out to red. Probably optimum for going into tissues is about 650, 800, that kind of area. But maybe you don't want it to go too deep, because if you're trying to cure bladder cancer, if you go too deep through the thin tissue, you might damage the normal tissue. So it's a kind of balance, and of course it will differ from tissue to tissue depending on how much hemoglobin. Natural chromophores, of course, will absorb the light, and that might differ from tissue to tissue. And the other thing to say perhaps is that, as many of you know, that the design of optic fibers and other things that would deliver light is improving all the time. The availability of lasers that can fire not only one photon but two photons, and so we might use two red photons to excite a molecule that has absorptions in the blue region, for example. So this is really work in progress of people trying to use not just one photon but maybe two or three, fire them very fast from a laser, and they'll add up to produce higher energy light that would excite the molecule of interest. So this is a kind of Jablonski diagram, if you like, where we excite an electron. If the spin state doesn't change, you go to a singlet excited state. There might then be intersystem crossing, which might be helped by a heavy metal in the molecule to a triplet state. And then, well, it might be actually from the singlet, you might get emission of heat. This is then photothermal therapy. I'm not going to talk about that. We don't do it at the moment, but this might be, people are using gold nanorods, for example. You can heat up local tissues by, I don't know, 10, 20 degrees even sometimes, and kill cancer cells that way. It looks very promising. I'm going to talk about this photoactivated chemotherapy. That's where in the triplet state, we change the bond lengths, we weaken bonds, and molecules can be released and can kill cancer cells through being released from your pro-drug. And over here, from this triplet state, is what is in the clinic at the moment, as we'll see in a moment, called photodynamic therapy. So this is the main mechanism of killing the cancer cells, is to transform ground state triplet oxygen, then into excited state singlet oxygen, which is very toxic and will kill cancer cells. So there's these three kinds of phototherapy here that are very much being investigated at the moment. So if you think about metal complexes then, and those of you that are familiar with crystal field theory, ligand field theory, will be familiar with these kind of diagrams where the metal itself with its 5 3D orbitals or 4D or 5D orbitals in a crystal field, when it put ligands around it, this would be like an octahedral field. So it would be a T2G set here, 3 orbitals that can take 6 electrons. So in a D6 system, like the ones I'm going to talk about, you can pair those up and you have a diamagnetic complex. You get nice sharp NMR spectra, and then you can shine a light and hope to excite one of these electrons to a higher energy. It might go into another higher energy d orbital and on the E or EG state up here. If it doesn't change spin, we get a singlet state. If it changes spin, we get a triplet state. So it's a metal-centered transition. We might have a metal electron being transferred onto the ligand. So metal to ligand charge transfer. Here we are, I've drawn some pi orbitals here on the ligand. So this would be a d electron going into a pi star orbital on the ligand. Or it might be the other way around. It might be a ligand electron. Here is a pi ligand electron here, this blue one. It might be put into an empty E orbital, EG orbital on the metal. Or it might be ligand-centered. It might go from one ligand orbital into another ligand orbital. So all of these transitions could play a role and could be very important. I should say here how much I value these days my collaboration with theoreticians, with computational chemists, with people who do DFT calculations, because increasingly DFT can really give us insights into these processes, and they're much more complicated than I ever thought they were. Anyway, you'll see some of my descriptions are rather hand-waving, but the DFT people try to put me right in much more rigorous descriptions of these transitions. So, photodynamic therapy is in the clinic at the moment in most of our major hospitals then, and the sort of prodrugs, the photosensitizers that are used are porphyrins like this one, photofrin, because it has this extensive pi electron conjugation system here. So you can excite this molecule, you can produce a triplet state, and a triplet state can convert ground state, triplet state oxygen into excited state singlet oxygen, and that is enough usually to kill a cancer cell. There are people who've made derivatives or variations on this because photofrin has some problems with purity sometimes, they tell me, and there is sort of here phosgan. You can see here we have a reduced, one of the pyrrole rings is reduced here, and then you can use levulan, which is a precursor for porphyrins. So by biosynthesis, you can convert this into porphyrins. So those are in the clinic at the moment and are pretty well used for surface cancers at least. For deeper cancers, they're in trials, many of them. And what's exciting for us inorganic chemists, I think, is that down here I've listed 2 new compounds that are in clinical trials, and they're both metal complexes. I think the next slide I put the structures is TLD1433 and WST11. TLD1433 is Sherry McFarlane and co-workers. You can see it's a ruthenium tris-bipyridyl complex. Those sort of tris-bipyridyl complexes have been known for many years to have interesting photochemical properties, and they're relatively stable when you excite them. Nothing falls off, and they're relaxed to the ground state, so they can act catalytically. And McFarlane and colleagues have made some interesting design changes here, just small modifications, if you like, with this chain of thiophene residues at the end here. And this is in trial now for bladder cancer. And, over here, there is now, well, this is actually, what do they call it? It's a bacteriochlorine, I think. It has 2 reduced pyrrole rings here, one reduced up here and one reduced down here. Now, this is well into clinical trials for prostate cancer. So again, you start to think, how will you deliver light to internal organs? And actually, I've seen pictures with people with holes dug in their skull to get light into the brain for phototherapy. So, you know, you can get light into all sorts of places these days. So I think this has a lot of potential. We'll see how these go in clinical trials. So I mentioned a couple of studies we've done on ruthenium too. Here is one. This is a bis bipyridine complex then, just 2 bipyridines on ruthenium-2. Now, instead of another chelated ligand, another bipyridine on this side, we have monodentate ligands, 2 pyridines. And this is a rather special pyridine. It's a drug called isoniazid. Isoniazid is used as an anti-tuberculosis drug, but people are worried about the resistance to that drug in the clinic, and it would be good to have new derivatives that can avoid the resistance with the isoniazid itself. So we synthesized this, at least Nicola Smith did when she was a PhD student in my group, with the help also of Pingyu Zhang, and particularly with the photochemistry with my colleague Bas Stavros, who has fast lasers and so on. And the interesting thing about this is if you excite it with blue light, very quickly, and when I say quickly, you know, this is picosecond, nanosecond. This is something that's always really excited me, the fact that you can release ligands very quickly. And of course, once you excite electrons in your molecule to other orbitals, you can weaken bonds. And so you can release this isoniazid very quickly. And the question is this useful for killing bacteria? And the calculations tell us that it's a metal to ligand transition, but it's the transfer of both those unpaired electrons onto the metal itself, which leads to the release of one and then the second isoniazid. And when Nicola Smith designed this little setup here, where we can put bacteria into wells in a plate, and we can irradiate them with various lights, LED lights, and so we can determine the effect of irradiation on the activity. And you can see here, I'll just go to the blue LED with blue light. It's 10 micromolar, so that's half what you'd use for that, because there are 2 isoniazid ligands. You can see that it's pretty effective at killing. Well, we used Mycobacterium smegmatus. It's a similar kind of to the tuberculosis mycobacterium, but of course it's much safer to use it in our lab. So that was encouraging, I think. 5 times more potent than isoniazid itself. So encouraging for developing antimicrobials based on photoactive compounds. And if you're more interested in the mechanism, a few years ago, with the help, again, of theoreticians, the calculations show that when you excite into these ruthenium BP complexes, you go to a triplet ligand metal state first, but then there is a transfer into this triplet metal-centered state, and that's where the bond lengths increase. And I put a little diagram down the bottom here to show you that in this triplet metal-centered state, that the ruthenium-nitrogen bond lengths increase by, you know, up to here, up to 2.8 angstroms. So they get weaker, and that's why there is release of these coordinated ligands. You can actually get release of a chelated bipyridine ligand if you put enough steric hindrance near to the nitrogen, so you can control actually release even of a chelated ligand on ruthenium when you activate it by light. Here's a different kind of release. This is a ruthenium-2 half sandwich complex of the type people use in transfer hydrogenation complexes. We made a lot of those in our lab, and this work was with the group of Vicente Marchand in Barcelona. And you can see here the receptor targeting idea, that you can conjugate one of the ligands, a pyridine derivative again, to octreotide, which is a somatostatin antagonist, or RGD, that's arginine glycine aspartate. And both of these have receptors on cells. And what you're looking for, of course, is more receptors on a cancer cell than a normal cells. That's what you're looking for if you want to target to cancer cells in preference to normal cells. You can see a new thing happened. It wasn't just the pyridine that came off. That did come off, but also we were able to photo-release the arine, this pi-bonded paracymene on here comes off, and now you can bind to DNA and can get some unusual lesions on DNA. So that's another interesting release and another way of attacking, in this case, DNA now inside a cell. Okay, let me go on now from ruthenium 2, jumping over to platinum 4, and okay, back to basics, if you like, to cisplatin. For those of you not familiar with platinum drugs then, cisplatin was the first into the clinic in about, what, 1979 or so, still widely used. And the important thing here, I guess, is the design, because transplatin is an isomer, the two ammonias are trans to each other, but does not kill cancer cells. So clearly, the stereochemistry is very important. So carboplatin was into the clinic as this next generation, followed by oxaliplatin, so two more platinum drugs. And between them, these three drugs account for, I think, something like 50% of all chemotherapies for cancer use one of these platinum drugs. This is a nice little vibrational calculation of DFT given to me by Julius Woolney in Kaiserslautern in Germany, who we work with quite a lot. And it sort of illustrates, doesn't it, where the weak parts of this molecule are. So these are the platinum 2 chlorine bonds that break, and these are the bits that bind to DNA and cause the changes in the shape of DNA that cause the DNA to bend, and ultimately it causes the cell to die. But wouldn't it be nice to have a platinum drug that didn't cause size effects, because these compounds will attack normal cells as well as cancer cells. If only we could produce a non-toxic platinum complex that really was targeted mainly at the cancer cells. So that's what we tried to do when I was in Edinburgh. Philip Müller came to my lab, a Swiss PhD student, and started working with Patrick Begnarski's group in Germany. Patrick had this idea of platinum prodrugs based on the absorption of light and photoactivation, but the complexes he had were iodido complexes that really weren't stable enough to reach the target sites in cancer cells. And so Philip Müller and I and one of Patrick's PhD students, which came to me as a postdoc, Nicole Catcherville, we started to make these azido complexes here. Look, they always look a bit weird, don't they? 3 nitrogens in a line, 2 of those on platinum. And the idea here was to have a cisplatin prodrug, really, that when we photoactivated this, we thought we would release the actual hydroxide ligands, and we thought this would be ligand to metal charge transfer. In other words, 1 electron from hydroxide, from each hydroxide, would liberate hydroxyl radicals, and then here we would have platinum 2, and the platinum 2 would be more reactive. And we made several of these complexes. Importantly, Philip Müller found that in the dark they were stable, even in the presence of glutathione. And remember, inside cells, you've got high concentrations of this thiol, that's gamma-glutamyl cysteine glycine, and heavy metals like platinum are very reactive normally towards thiols, and it was stable. So that was good. We might be able to photoactivate this inside cancer cells. Well, we've made a lot of complexes in this sort of series. To cut a long story short, we could shift the wavelength of absorption a little bit more into the visible from the UVA region by having not cis complexes, but trans complexes. Now that seemed to disobey all the rules of cisplatin activity, if you like, right? All the complexes that were patented early on. They all had a cis configuration, 2 nitrogens, 2 amines cis to each other. Here, this is the work of Yao Zhao, now a Chinese PhD student in my group here, now has his own position at the Chinese Academy of Sciences in Beijing. And we worked quite closely with Nikki Woods in Dundee Hospital, 9 Miles Hospital, Julie Woods at 9 Miles Hospital, Dundee. And also this was Nikki Farah as a postdoc, and of course much more help with this work. Victor Brabek, we've collaborated very closely on with DNA studies, for example, in the Czech Republic and his group. So we're very grateful to all of them. So yeah, I made these trans complexes, and here you have 1 pyridine, and here you have 1 methylamine. You can see here, and these are very active. You can even put a thiazole over here. And importantly, like most of these complexes that we've been making in this series, they're not cross-resistant to cisplatin. They must have a different mechanism of action, potent against a wide range of cancer cells, ovarian, esophageal, for example. And they cause very different lesions on DNA to cisplatin. And they cause big changes in DNA structure, again, different from cisplatin. So they're not cross-resistant to cisplatin. I show you this because this is still, to me, an interesting observation that Yao made, that when you excite this, for example, with blue light or UVA, you can detect singlet oxygen being produced. Now, what I'm going to tell you is really that these complexes do not need oxygen for activity, so they're different from the normal photodynamic therapy agents, and that might be good because a lot of cancers, a lot of tumors are deficient in oxygen, they're hypoxic. So we don't really want to rely on oxygen for killing the cancer cells. If we have independence of oxygen, it would be good to have that as well. So, but these seem to produce oxygen even in the absence of oxygen. Even under argon, you see here. We still don't fully understand how that works. Presumably, it's from the hydroxides or the solvent that you obtain the oxygens to make singlet oxygen. So it's still very interesting, but this is an interesting aspect of its mechanism. Now, what Yao did was to react this compound with guanosine monophosphate and to irradiate it with blue light. And he was able to detect here, is that bar at the top hiding part of my screen? It is on my screen, but it might not be on yours, I'm not sure. Nobody's answering, so either nobody's listening or it's okay. Okay. Can then somebody tell me whether that black bar at the top is hiding part of my slide? You don't see a black bar?
No, we don't.
Okay, that's good.
It's fine, Peter. We can see everything. Yeah.
Okay, I have to remember what's under the black bar. So under the black bar is actually an azide ligand still on platinum. So in this case, one hydroxide must have produced one electron to donate to platinum and one azide. Well, that's okay. And you can see here you get a bond here to N7 of guanine. So this could attack DNA, guanine residues. But also Yao found an ammonia ligand. Where does that come from? Well, we think that must come from release of nitrogen by a bound azo ligand and formation of a nitrene, which gets converted into ammonia. So another interesting pathway here for this drug when you turn the light on. That's why I say photochemistry of metal complexes is a real challenge, right? There are pathways here that are several and various, and we have to know how to detect them and so on, which is quite a challenge. So here's one compound we've done a lot of work on then. This is particularly Nikki Farah here, who found a good synthesis of this compound. 2 pyridines in the trans position, 2 trans hydroxides, 2 trans azides. Stable, water soluble, non-toxic in the dark. It doesn't kill a whole range of cells, mainly absorbing here down in the UV region. Apparently very little absorbance up in the visible region. And again, this is really interesting. And we've tried to look at this with calculations, but we can activate this compound with blue light, sometimes with green light, but there's almost no absorption there. How does that work? Maybe there are some very broad bands there. That's what we came to the conclusion with Rob Deeth, who's a DFT specialist. Very broad bands that are solvent flattened, we can't see, but we don't understand this very well. And the transitions that we call ligand to metal from azide or hydroxide are actually quite complicated. You can see there are several bands under there. It's not just a single transition. When we turn the light on, this happens to be UVA here. Okay, we kill these cancer cells, ovarian, esophageal, liver cancer cells, at low micromolar doses. So that in itself was encouraging to suggest that we might be able to use this as an anti-cancer complex. Victor Brabeck looked at the binding to DNA, and again he found that some unusual DNA adducts which inhibited the transcription of DNA by stalling an RNA polymerase. We looked into the adducts with DNA in a theoretical way with, again, with Rob Deeth. Rob Deeth and I had a joint student, Hoi Chung Tai, who worked between our groups and modeled what would be the lesion on double-stranded DNA caused by what would be a platinum 2 transpyridine. So here we have a platinum. There are two transpyridines on this. You can see them coming out and going into the plane of the slide. And here are two guanines on opposite strands of DNA now. So it's producing an inter-strand cross-link. So quite different from cisplatin. So quite a different kind of lesion. And it's producing quite a big bend, 67 degrees, and quite a lot of unwinding of the helix. So those are unusual lesions, and perhaps not surprising it's not cross-resistant with cisplatin. Now, this is work of Jenny Butler, a PhD student in my group, who thought that if azide radicals were being produced, in other words, we're donating one electron from bound azide onto platinum-4, we should produce an azide radical N3 dot. Can we trap it? So we add a spin trap, DMPO, put it in the EPR machine, irradiate it with blue light, and we're fortunate to have very good EPR in our physics departments as a help of my physics colleague Mark Newton. And you can see here, this was very successful. We were able to just put this pyridine complex in a pH 7 buffer, add the spin trap, irradiate with blue light, and you got this very nice pattern that enabled us to identify a spin-trapped azide radical. Jenny went even further. She labeled the azide ligand with 50% N15 rather than just N14. N14 then has a spin of 1, so you get triplets here. N15 has a spin of a half, so you'd get doublets. So 50%, you get a mixture of doublets and triplets. So that shows you that azide radicals could be produced inside cells. Maybe they're helping to kill the cancer cells, as well as the platinum-2 that's produced. Well, this was another interesting observation then. What she did was add tryptophan to this solution. With no tryptophan, she could trap the radicals. When you added tryptophan, even at 1 millimolar, you completely quenched the radicals. So that means that azide radicals perhaps could attack tryptophan residues inside the cell, and that would be really interesting. And in the last few years, we've gone on with Mark Newton's help again to get a special trap that will trap tryptophan radicals and show that, yes, that is the case, that azide radicals will take an electron from the indole ring of tryptophan, and that can deprotonate. And you can see these red signals here are characteristic of tryptophan radicals. So maybe we can interfere with electron transport processes in cells, because tryptophan is often involved with electron donation and acceptance across electron transfer chains. Well, we went on a bit further to look at some biopeptides. Here is substance P, here is bombasin, a couple of peptides. This substance P has no tryptophans. Bombasin has a tryptophan in the middle, you can see here. So we took this pyridine complex. This is the work now of a PhD student, Chris Wotton, who was jointly between myself and Pete O'Connor at Warwick. Pete O'Connor has then Fourier transform MS. This was done on a 12 Tesla. He now, in the last few weeks, has got delivery of a 15 Tesla FTMS instrument. Very powerful, excellent sensitivity, excellent resolution, sort of thing. It's great for doing analysis of biological solutions, especially when they've got metals in them. Even he gets very excited by metals that have lots of isotopes. We have special programs that pick out metabolites with metals like platinum in them. But you've got to be very careful with the experiments. You're very careful, you know, mass spectrometrists often throw in a bit of acid to make sure they've got a positive charge, but we mustn't do that because it might release the platinum from these metabolites. So we have to be very careful how we do the experiments. Be very careful how we fragment the products, because if you fragment them with traditional methods like collisionally activated dissociation, CAD, or IRMPD using infrared photons, then you get large loss or some loss of platinum. You've got to be very careful that platinum doesn't get lost in the mass spec instrument. And so particularly we found very good was electron capture dissociation. It turned out to be very good for fragmentation and retaining the platinum on the adducts with the peptide. So substance P, we found oxidation of methionine. Adding an oxygen atom at the sulfur, then you can get a sulfoxide. You could even add 2, but we found mainly 1. But bombasin then has the tryptophan. And sure enough, we found that you can add an oxygen atom to tryptophan as well as the methionine in bond basin. But think how complicated that suddenly makes your analysis, because in fact you can add one oxygen or two oxygens to tryptophan plus adding an oxygen of methionine. You suddenly get a whole mixture of things that might occur. But this sort of thing might occur inside cells. So this multi-modification of peptides and proteins inside a cell might be very important for killing cancer cells. And the mechanism seemed to be via hydroxyl radicals in this case. The pathways of tryptophan oxidation seem to match the sort of other products we saw were sort of typical of what people see for hydroxyl radical attack. We went on one stage too far because we still haven't published this because it's too complicated. This is a real protein. This is, if you can call lysozyme a real protein, but at least it's a model protein, isn't it? We can take the platinum compound again, add it to lysozyme, 14 kilodaltons, irradiate it with blue light, and indeed you can see various charge states of lysozyme. Then you can irradiate it, and now you see 5,600 peaks and 400 species. You can imagine how this might work, can't you? Because the methionines, there's tryptophans, there's platination or no platination. But this is what we have to face up to, and the information is there. Maybe now we've got 15 Tesla machine, we'll start to sort this out. But that is the challenge, really. I actually find this quite exciting, but it is a complicated thing to think about. In vivo, these compounds seem to work. This is work done at Nine Wells Hospital again, with one tryptophan, one pyridine now, and one ammonia trans. And you can see here that if you irradiate this mouse when it's been administered the platinum compound, it's much more effective at reducing the size of this esophageal cancer. Remember, esophageal is a relatively surface cancer like bladder cancer, so even blue light might be very good for that. And this is, this is blue light for short times. This is only about half an hour, 2 times half an hour. So this is short irradiation periods. Julie Woods used to say to me that some of these doses are a bit like sitting out in the sunshine in Scotland for half an hour. So these are not huge doses that we're using. So that's encouraging in a model of cancer. The other thing that I think is fascinating is the recent work we've done with Victor Brabeck. Again, work of Chinsri Imberti and Hannah Bridgewater in my group and people in Victor's group, showing that cell death, when we irradiate this pyridine compound with light, has all the hallmarks of immunogenic cell death. In other words, if you're familiar with this, there's calreticulin expression at the surface, release of HMB, high mobility group protein 1, secretion of ATP, autophagy, cell surface, ecto-CRT, and particularly, this is the bottom line, engulfment of photoirradiated C26 colorectal cells by macrophages. So this whole idea that you might be able to administer a compound, irradiate it, and that would vaccinate someone against future attack by cancer, I think is quite an exciting prospect. If we want to deliver these compounds then just to cancer cells, if we could, we might want to add a targeting agent, and these compounds are well set up for doing that, right? Because we can derivatize one of these hydroxides very easily. Here is an RGD, and RGD receptors, integrins, are found more on some cells than other cells. So here's 2 types of cells here. Here's a melanoma and a prostate, and you find more of this particular alpha-beta receptor on the melanoma cells. Sure enough, more platinum is taken up by those melanoma cells, and it's more toxic. There's higher potency in those melanoma cells than there are in the prostate cancer cells. Here's another one. Here is, well, the idea of this was a formulation really to make a gel. So this is the work of Venkatesh. We submitted this work to JSCS, right? And he wouldn't let me submit the paper because Venkatesh is an Indian and he only has one name, and you cannot submit a paper to JSCS if you only have one name. So he calls himself V. Venkatesh because then we can submit the paper. So this is very nice work by Venkat. And you can see here, putting a sort of catechol here, you can make a borate here, a bischelation here. you make a gel, basically. You see, this is a tube turned upside down. Look, the platinum gel is at the top of the tube. So that might be good for administration of this onto a surface. And it was highly reactive here against cisplatin ovarian cancer cells, 3 micromolar, and high selectivity for cancer cells versus normal cells. So on to the final section of my talk then, on to iridium-3. And this is work particularly started in Sun Yat-sen University by Hui Chao and his group, and a postdoc from his, or a student from his, from Sun Yat-sen, Pingyu Zhang, and Hawaii Huang spent time in my lab. And we made these sort of complexes here with 2 NC whoops, let's go back, didn't mean to go on. 2 NC coordinated ligands. So that's a C minus and a nitrogen on the iridium. Here C minus and nitrogen. And here is a chelated acetyl acetonate here. I won't say much about these sulfur bond one. Well, we also looked at these, but I'll talk about this acetyl acetonate complex. So these have very nice photochemical properties then, okay? 1 photon activation at 458, or 2 photon with red light. So that's encouraging. You might be able to use highly penetrating red light to activate this compound, even though it's best done blue light. And the lifetimes can be quite long, can be up in the thousands of nanosecond here. So that's good for luminescence, for example, or for passing on the polarization energy to other molecules like oxygen. Importantly, they will generate singular oxygen efficiently, and they're fairly selective for cancer cells versus normal cells, and are active at micromolar doses even in spheroids. So this is like a solid model for a solid tumor. Cancer cells clumped together into a spheroid with two photon again, rather than 1 photon, highly active again. So this was all very encouraging for these iridium-3 complexes. We asked the question, how do they attack cancer cells? If we put them inside a cancer cell and irradiate them, what's the damage that's done inside cancer cells? So again, we set us this difficult challenge, and that's with the help of Cooks and Chio. Again, was a joint student between myself and Pete O'Connor, and we had great help here from Martin Patterson and his co-workers in Harriet Watt, who are DFT experts. I'll come to that in a moment. And so we treated, in this case, lung cancer cells with this acetyl acetonate type compound here. And then we irradiated, or you have to have appropriate controls with no irradiation. That's what makes this experiments quite difficult, of course. You've got to choose your dose, you've got to choose your irradiation time, you've got to do it in the dark and in the light, quite a lot of work. And then you've got to sonicate the cells, you've got to extract the proteins, you've got to fragment them chemically, enzymatically with trypsin, make peptides, desalt those, put them into in this case, an FTMS machine, a 12 Tesla machine, and we detected 1,500 peptides and assigned them to 212 proteins. But that was quite productive and informative, because we detected specific damage to proteins like heat shock protein 70 and aldose reductase, 2 proteins that are, well, heat shock protein 70 is involved in chaperoning other damaged proteins in cells that are damaged by oxidation. Aldose reductase is part of the glucose metabolism system. And it's very interesting that you get specific damage on these proteins, which we identified by FTMS as an insertion of an oxygen atom at the 2 position of histidine, in this case with HSP, histidine 332, in case of aldose reductase at histidine 188, which makes you think, about targeting damage, even though it might be produced by single oxygen or even hydroxyl radicals, and getting a pre-association between your complex and a particular protein. You might be able to target the damage inside cells before you photoactivate, if you can get a complex to form between the 2. Now, the sort of things we're doing then also to look at the chemistry inside cells is using synchrotrons. Today I'll talk about diamond synchrotron. There are other synchrotrons around the world where you can do this kind of work. I just put a couple of them here. So this is a circulating beam of electrons that gives off high intensity X-rays. And you look at X-ray absorption, you get an edge which tells you about the metal itself or other atoms, even bromine, chlorine, etc., about the element then, and the fine structure that can tell you about the nearest neighbors. So you get structural information about the coordination sphere here, so Zanes and Exas. I won't talk about much of these today. We are doing this kind of work, and we have a paper that hopefully will come out soon, and next time I talk to you perhaps I'll be able to tell you more about this kind of analysis of the compounds I'm talking about inside cancer cells, because we are doing that kind of work. But I will tell you some other things. I'll talk mainly about the lighter atoms today, carbon and nitrogens. They are what we call soft X-rays. They don't require too much energy to excite the absorption of those. But you see, the nice thing about X-ray absorption or X-ray fluorescence, each element has a specific energy. So you can tune your X-rays beam into a specific element. If you want to look at platinum, you know where to look. If you want to look at iridium or osmium, etc., you can tune it. So you can pick out the absorptions from particular elements. That's really very powerful. All we got to do is learn how to do that with intact cancer cells. Now that's the tricky bit. I'll mention that a bit in a moment. So I'm going to look at this iridium complex now, because that's one we've published on recently. This is an NC ligand again. It's the one I've shown you before with the chelated acetylacetonate ligand here. And we're going to look at what happens to this when we photoactivate it inside cells. And we're going to ask really what damage it does to cells, and can we detect that? So this is the work of Lizzie Bolitho, who's just finished her PhD in my lab with the help of Hawaii Huang and particularly Carlos Sanchez and other people. Again, this is really the people at Diamond Synchrotron, Paul Quinn, Maria Hagliolaki, all very important people and really very skillful collaborators. We're very fortunate to work with these people. So Lizzie takes cancer cells then and irradiates them in the presence of this iridium complex. And then we can see inside the cancer cell. We can ask what's happening to the nucleus. And here we can ask, today I'll show you what happens to the mitochondria, the powerhouses of cells, right? These are where the electron transport chains are. This is where the oxygen is being turned into water and the ATP is being produced in cells. Quite a lot of work. I won't go through it all. Putting the cells onto a grid, fetal cast serum, seeding the cells, growing the cells on the grid, drugging them. You might want to add some mitotrackers so you can see the cells under a fluorescence microscope. You got to then freeze them very quickly. Now we don't always do it this way. We have done experiments where we fix them and embed them and section them. But with metal compounds, this is how we really want to be doing this. It's difficult though. You got to drop them into liquid propane very quickly. You don't want ice crystals to form on the surface of the cells. So this is the tricky part. And then you've got to get them onto the synchrotron beam line. Once you get them there, you get some amazing data really. With these soft X-rays, you can see ultrastructure. You can get resolution down to 25 nanometers now, right? So you can really see individual organelles. You can see processes going on the membranes inside cells. And you can tilt these cells, right? You can tilt them -65 to +60. And by reconstructing the information you get from the tilts, you can get three-dimensional pictures of the inside of these cells. And in particular, we can think about looking at the mitochondria inside these cells. There's quite a lot of them, but some dramatic things happen when we put this photoactivatable complex inside the cancer cells and irradiate. You can see it from this diagram already, that the treated ones and irradiated ones have much smaller mitochondria than the untreated or the control cells. So already you're getting some interesting information about what's happening inside the cancer cells. And I think I'll go straight on. I have a little movie, I think, on the next one. If it works, let's see if it works. Will help you to see inside the cancer cell, and you can see the nucleus in green, and you can see in 3D now the mitochondria, and you can measure the size of these mitochondria. And in this particular study, you'll see when I go to the next slide that they decreased in size dramatically, sometimes by up to a factor of 10. So this is quite a remarkable result that we can get now. We can begin to look inside cancer cells. So I say we are doing work at the moment looking at the metal itself, the iridium, the platinum, and this is a long job now to analyze those data, and it's taking us a long time. We still haven't got anywhere near finishing. I hope next time I talk to you, if you're interested, I'll be able to tell you about that. So a couple more quick studies. Pingyu Zhang, Hawaii Huang, again in my lab. Samir Banerjee, who was a postdoc in my lab, particularly Chintu Imberti. This compound now, here is phenyl pyridine again, C-N, 2 of them, but now monodentate pyridines here with a maleimide, a reactive maleimide in the side chain. React this with the protein serum albumin. Serum albumin has one reactive cysteine, cysteine 34. So you can attach this iridium complex to cysteine 34, at least it will attack, and you see here that it also seems to be involved with histidine 39 because the luminescence of this complex increases dramatically when a histidine is near to this complex. We don't fully understand that, but there's a dramatic enhancement of luminescence of this complex. You can see it here when we add human serum albumin, we get this dramatic increase in luminescence. So, interestingly, you can look at it inside cancer cells, and you can see inside the cancer cell.
Peter, I'm very sorry to interrupt you, but we have to keep an eye on the time. I'm afraid I have to ask you to go to the conclusions.
Okay, I'm going to go to the conclusions. So I'm going to show you that what I would have shown you is photocatalysis in my last few slides. So this is a new complex now with NNN triple chelated complex here, but and it's a very strong oxidant in the excited state. It will take an electron from NADH to form NAD radicals, and we can trap those radicals in the EPR, and we can study it, and we can show that the NADH level goes down. So it works under normoxia and under hypoxia, because not only can we form single oxygen, but we can form these NAD radicals, and we can get catalytic oxidation, catalytic reduction of cytochrome C by this system here. But I can let you read about that because it was published recently in Nature Chemistry, and this is a really totally new mechanism really now inside cells. We think not only single oxygen but also oxidation of NADH forming NAD radicals. So I've shown you ruthenium-2, release of anti-tuberculosis drugs like isoniazid. I've shown you platinum-4, there's hydroxyl radicals, the Z-di radical specific attack on DNA and proteins. I've shown you now iridium-3, single oxygen, oxidation of specific histidines, luminescent imaging, albumin delivery, NADH, NAD radicals, and catalytic reduction of cytochrome C. And asking these questions about, can we follow this kind of photochemistry inside cells, and how we're trying to use synchrotron methods for doing that. I mustn't forget the funding bodies, because they're really important in this kind of work. It's always expensive to do, and I thank all of these people for doing that. I didn't list the people, and it's now you have to go a couple of years back because we haven't all been together in the same room for a long time. But we show you some of the people here, like Lizzie Bolitho, who did a lot of that synchrotron work and so on. Won't go through them all. But thanks very much for all of these people who've done the work. And thank you all very much for listening.
Okay, thank you very much for this nice lecture showing the use of all these different metal complexes for phototherapy. And especially, what you presented in the end to see actually the mechanisms that are going on in the cells. It's very challenging and very interesting. I see a hand raised by Shupik.
Yeah, Peter, thank you very much for this very inspiring chemistry. So I have several questions, but I don't think I'll be able to get that much time. So I start very quickly, ask you the questions. So one question is that in your very last presentation, last slides, you have shown that superoxide radical anode can also be used for, let's say, for the photodynamic therapy. However, we know, I mean, that singlet oxygen is the key species, but you actually change that opinion, I would say, and which is absolutely fine, inspiring, I would say. Now my question is, so what is your opinion? For the singlet oxygen is super reactive. Compared to that, superoxide radical anion is less reactive. Do you think it's the kind of advantage for controlling the selectivity in the cell?
But possibly. It's so complicated, isn't it, that it's difficult to sort of say yes or no, isn't it? Because it depends on the local region of the cell in which these reactions are occurring, doesn't it? That's something I always need to think about as a chemist. There's so many different compartments in cells, whether they be in organelles like mitochondria, even within mitochondria. Is it in the membranes? Is it in which part? You know, there is so, and we know for photochemistry that it depends a lot on the medium, right? We change the solvent from water to acetonitrile and so on, and we see dramatic changes in the luminescence, the quenching, and so on. We know that the medium is very important. So the polarity of that medium and the actual reactivity of the medium is very important. And the first step, I guess, is to try and detect what we are looking at so that we can try and understand the chemical reactions. But it's a good question and something we will have to pay more attention to, I think.
Peggy, can I ask a very quick second question?
Yes.
So along the same line, actually, for say the light should be also one of the very, let's say, controlling factor in this.
Yeah.
You need one side, you need a stronger light to activate your photosensitizer or photocatalyst, and on the other hand, if you have very strong light, it can kill your cancer cell.
Absolutely, because if you start using UVA, you're more likely to do damage to your cells than you are for longer wavelength light. And there's then a question of moderating the dose that you use, isn't it?
Mm-hmm.
And obviously, in our own labs and our own experiments, we use control experiments, so we keep a check on the toxicity towards normal cells. Yeah, I mean that's what we do. So you're right. On the one hand, you want to produce very active species to kill cancer cells, but you don't want them to kill normal cells. Yeah.
Okay. Thank you, Peter.
Okay, time is limited, and I see a few questions in the chat and in the Q&A. Let me see a question from Vikash Kumar. What is the difference exactly between photodynamic therapy and photochemical therapy, and which one of the two would be the best?
We only keep the term photodynamic therapy really just to give the older systems their recognition, if you like, because that's what people used to call them. And it used to be said that they are mainly and only involve conversion of triplet oxygen into singlet oxygen. But even some of the new reagents like TLD1433, I think are mainly photodynamic on that, but also probably have other mechanisms as well. And the reason we call them photochemotherapeutic agents, really, our platinum compounds are there to produce cytotoxic species rather than singlet oxygen. It happens that they can produce singlet oxygen. So there's this big continuum, if you like, and you can use phototherapy for the whole range if you want, and it won't be a problem. And it would be a mistake to assume that systems only do one thing, I think. But as whether it can be an advantage depends on what you're trying to do, I think. Could be an advantage to have many mechanisms for killing your cancer cells because that avoids resistance pathways.
Okay. Thank you very much. I think due to time restrictions, we will stop the discussion now. But Peter, if possible, if you can still take a look in the Q&A session and answer a few questions there. I think there are still 2 more questions. To answer them in written form, that would be very much appreciated.
Okay, thank you for listening.
Okay. We thank you once more for your interesting and inspiring lecture, and then let's move on to the last talk of today.
Yeah, thank you, Peggy. Thank you, Peter. So now we have our very last speaker, Professor Oliver Wenger from University of Basel. So Professor Wenger actually received his PhD degree from University of Bern in Switzerland in 2002, and he worked with Professor Hans U. Gödel Following his postdoctoral research at Caltech with Professor Harry Gray and University of Strasbourg with Jean-Pierre Chauvet in 2004 to 2006, he became assistant professor at University of Geneva in 2006. In 2009, he moved to the University of Göttingen in Germany as an associate professor. And then in 2012, he actually went back to Switzerland to join as the full professor at University of Basel, where he is currently promoted to a full professor in 2018. So with this information, I kindly invite Oliver for presenting the chemistry with the multi-photon excitation in photocatalysis. And Oliver, screen is yours now.
Thank you very much, Shubik, for the kind introduction. Also, many thanks for the invitation to both you and Peggy. It's a pleasure to participate in this online symposium. When my group and I engage in photocatalysis, then usually in a context of physical inorganic spectroscopy, we have a mechanistic interest in understanding photoredox and energy transfer reactions. And out of this research, I will talk about 3 specific projects today. First one on the photogeneration of hydrated electrons using the consecutive absorption of 2 visible photons. Then photocatalysis via triplet-triplet annihilation upconversion, a subject that has received significant attention also from the synthetic photoredox community lately. And finally, a brief section on photochemical hydrogen atom transfer as opposed to the classic single electron transfer chemistry that one usually encounters. This here is iridium PPY. This is a fairly well-known nowadays commercial photosensitizer and photocatalyst, which is very lipophilic. It's well suited to conduct many different types of organic photoredox reactions, is however very poorly soluble in polar solvents, and it's essentially insoluble in water. And in a project that preceded the one that I will talk about today, we had a collaboration with an enzyme chemist who wanted to do combined photoredox and enzyme catalysis. So we had a need to make a hydrophilic variant of this strongly reducing iridium phenylpyridine complex here. Through silvination, this is relatively easily possible. And this compound has very typical photophysical properties for this compound class. You see a UV-vis absorption spectrum here, the black trace. You can excite here at 430 nanometers, for example. And you will see photoluminescence from a so-called metal to ligand charge transfer, MLCT excited state. In this MLCT state here, basically an electron is promoted from a metal-based iridium orbital here out to a ligand-based pi star orbital. So formally you have a reduced ligand and an oxidized iridium 4 center. And upon return of that electron back to the metal core, there can be photon emission, which is seen here. This is a spontaneous decay that you observe after pulsed excitations here, the MLCT luminescence. This is very, very classical. Now, whilst that MLCT state is present, you can also record an absorption spectrum by a technique called transient absorption or laser flash photolysis. And this typically gives you different spectra, but you can also do those types of spectroscopy in calibrated quantitative fashion, such as to get finally an excited state absorption spectrum. And this is what I am showing you here. This is more noisy than a ground state absorption spectrum because you can only excite a small fraction of your available iridium compounds to the MLCT state. But this MLCT state now has a distinctly different spectral signature than the electronic ground state. In particular, you notice here this absorption band around 500 nanometers, where we can now excite with a 532 nanometer neodymium laser to excite selectively the already MLCT excited species. And it's important to note that at 532 nanometers, only the excited state absorption, But the electronic ground state here, 532, is marked by the dashed vertical line here. The electronic ground state is completely optically transparent. So when you do a pulse sequence, you excite the time 0 with a blue photon at 430 nanometers, and then you wait some couple of 100 nanoseconds, and then you come with a secondary green excitation pulse at 532 nanometers. You will excite only the MLCT species with the second pulse. And as you can see from this panel here at the bottom, the second pulse here, which occurs after 400 or 300 nanoseconds in this experiment, some of the MLCT luminescence disappears instantly. You see the kink here where I have the laser point in the green trace. Immediately upon absorption of the second laser pulse, some of the MLCT population disappears. And at the same time, there is a new transient absorption signal at 660 nanometers, which I am going to assign to the hydrated electron on the basis of transient UV spectra that I will show you in a second. So the working hypothesis here is that we have a first photon that promotes the iridium complex to the MLCT state. The second photon then ejects the already excited electron into the solvent. You form a hydrated electron and you are left with an iridium-4, the one electron oxidized 4 compound of the initial starting material. Now, the spectroscopic evidence for that, or part of it, is shown here on this slide. You see here a difference of different spectra. This spectrum singles out the effect of the second of the green laser pulse. You see a bleach here in the UV, an absorption band at 600 nanometers. And this bleach and this 600 nanometer absorption here, they match up well with this black trace shown in the middle spectrum here. And this black trace was obtained in a spectroelectrochemical experiment. We simply took the iridium-3 complex and oxidized it electrochemically to the iridium-4 analog. So this is showing us the oxidation product. Now there is additional intensity here in the transient absorption spectrum near 700 nanometers, which cannot be explained by the oxidized iridium, which is, however, lining up very well with the reference spectrum of the hydrated electron. So on that basis and on complementary assays, chemical assays, which I'm not showing you today for time restrictions, we are assigning the photoproducts here as the hydrated electron and the one electron oxidized iridium complex. Then it occurred to us that if we now had a sacrificial electron donor that would re-reduce the iridium-3 back to the iridium, re-reduce the iridium-4 back to the iridium-3, then we could eventually close a catalytic cycle to produce hydrated electrons. Also shown here, this is the starting point corresponding to the compound here in its native form. First excitation to the MLCT state. Second excitation, ejecting the electron into the solvent to get the naked hydrated electron, the superreductant that we're going to use in a minute for photocatalysis. And then a sacrificial electron donor called DSAC here would take us back to the initial starting point to close the catalytic cycle. And this works not only in a pulsed laser experiment, but also in a steady state laser excitation setup, where now we use 447 as an excitation wavelength of a continuous 1-watt laser. And 447 lies in between these two wavelengths here, so that we can excite both the electronic ground state, but also the MLCT state and form the hydrated electrons. These hydrated electrons then, on the one hand, were used to reduce this trifluoromethyl group here to a difluoromethyl group here. We use a carboxylate here to get the water solubility, as we are restricted in this chemistry to aqueous solution with the hydrated electrons. We must somehow make our organic substrates water soluble, and this was the case here with these carboxylate groups. The sacrificial donor in this case here, triethanolamine, is one of the classic tertiary amines that many of you will be familiar with. Another reaction that works quite well with this strategy here is shown below. This is the decomposition, the photodegradation of these benzyl ammonium cations. This structural element here is present in many detergents, for example, in contact lens cleansing solutions and other things. But these benzyl ammonium cations are environmentally harmful. So they must be destroyed in wastewater treatment. And that currently happens typically via UV irradiation. But there are all sorts of issues associated with UV irradiation of wastewater treatment. So here we can do this with visible light, 447, to degrade these benzyl ammonium cations here to benzyl radicals and then onward reactions to biologically less harmful products. So this is a proof of principle study here that showed that the hydrated electron can be formed in catalytically relevant concentrations, and that this is a kind of chemistry that does not necessarily rely on high intensity pulsed lasers, that can, however, also work with more mild steady state irradiation conditions, such as the ones that we used here at the end. So with this, I'd like to switch to the second topic already about upconversion. And I'd like to stay for a minute in aqueous solution. I will make within this chapter the transition to organic solution and more organic synthetically relevant reactions, but would like to begin with aqueous upconversion. Perhaps just to illustrate or to remind everyone what triplet-triplet annihilation upconversion is. This is a process where you have a sensitizer on which you can excite a singlet excited state, which will then undergo rapid and efficient intersystem crossing, ISC, to a triplet state. And this triplet state is key. From there, you can now undergo triplet-triplet energy transfer to so-called annihilators. These are typically polyaromatic hydrocarbon compounds, such as anthracene or diphenylanthracene, which is shown here. And these organic triplet excited states, once populated, they have a really slow depopulation because their relaxation to the ground state is strongly spin forbidden. So you can build up large concentrations of triplet excited anthracenes. And every once in a while, two such triplets may collide in solution and undergo the process of triplet-triplet annihilation upconversion, whereby one of the two triplets donates its energy to the reaction partner. That reaction partner is upconverted to the fluorescent singlet state here, whilst the other reaction partner returns to the electronic ground state. So typically you use two input photons, two excitations, as emphasized by the two wavy green arrows here, in order to get a blue photon out of the system here to maintain energy conservation. As far as the simple photophysics are concerned, there are two key parameters here in such an upconversion systems. One of them is the excited state lifetime of the sensitizer. The longer the lifetime of that sensitizer, the higher the likelihood that you will be able to perform successful triplet-triplet energy transfer. And in terms of photophysics, really, rather than photochemistry, one key parameter on the acceptor annihilator is, of course, the fluorescence quantum field. And those are difficult to optimize in aqueous solution. We try to do that using ruthenium tris by pyridine as a benchmark system here, for which I'm showing you a transient absorption spectrum, also including the spontaneous emission here at 600 nanometers, showing up as a negative signal. And you learn from these decays here that this excited state in deaerated water solution at room temperature lives for about 600 nanoseconds. That's the standard lifetime that you can expect. And this is, however, relatively short for efficient triplet-triplet energy transfer, particularly in water. So we felt the need to optimize the photosensitizer. We have exchanged bipyridine ligands here by two phenanthrolines. And the most important modification here was to include a pyrene substituent here on the periphery of this bipyridine. And what that does is it lengthens the metal to ligand charge transfer emission lifetime by roughly a factor of 30. You see, we go from 0.6 microseconds to roughly 18 microseconds under identical conditions, owing to an effect called in physical inorganic chemistry the triplet reservoir effect. There's a reservoir here of organic triplet excited states. Here's a triplet pi star state, which is energetically close to the metal to ligand charge transfer excited state. And these states are thermally equilibrated. This one is very, very long-lived and helps to boost, to enhance the excited state lifetime here of this iridium, of this ruthenium photosensitizer. So this will be helpful to optimize upconversion quantum yields. The other factor that I mentioned that is key for photophysics is the fluorescence quantum yield. Typically in water, again, these carboxylate groups are used to solubilize. When they are attached directly to the core of the anthracene, this results in relatively poor emission quantum yields here. When, however, electronically decoupling here the carboxylates from the fluorescent core, then you can enhance the fluorescence quantum yields by roughly a factor of 8. And when you then combine these two effects, the triplet reservoir effect and the fluorescence quantum yield enhancement, then all of a sudden you can begin to see relatively decent upconversion in aqueous solution. But this remains a very, very inefficient process. Here I have specified the upconversion quantum yield here under optimized conditions. This number means that basically under when 100 photons, for 100 green photons that are absorbed, you will only get one upconverted photon. And this is low compared to organic solution. In organic solvent, these quantum yields can be significantly higher, but a few years back here, 3 years ago, this was the record in aqueous solution. And we were then curious whether this fluorescent excited state generated via upconversion could actually be exploited also chemically. And it shows a relatively straightforward benchmark reaction here, the reductive dechlorination of trichloroacetate here. It's a reaction that requires a fairly negative reduction potential, minus 1.9 volts, versus NHE in water. It's very reducing. And we can, however, expect from these singlet excited anthracene derivatives here reducing abilities that should be competent to lead to the reductive dechlorination. And that could be confirmed in an experiment using chloride sensitive electrodes. So we actually detect here the chloride anion with a specific electrode where we can do quantitative measurements. So this is again proof of principle reaction where we show that a fluorescent excited state here generated via upconversion can do a photochemical reaction here, the reductive dechlorination of trichloroacetate. And the fluorescent excited state is formed, as I showed you on the previous slides here, via triplet-triplet annihilation upconversion. Ruthenium is excited, triplet anthracene population is built up, and then ultimately the fluorescent highly reactive excited state is formed. And this work that we did here in aqueous solution is somehow related to a mechanistic debate in multiphoton excitation-based catalysis, which was initiated by my colleague Burkhard König in Regensburg, who published along with his group in 2017 this paper here in Angewandte Chemie, Sensitization Initiated Electron Transfer for Photoredox Catalysis. Paper was very well received, has attracted many citations until now. Is obviously a reaction that seems to be of significant synthetic use here. This is a CH arylation reaction type here, where the substrates are chloro and bromoarenes, which then undergo reductive dehalogenation using a Rubipi photocatalyst and the pyrene co-catalyst. And in the presence of a radical trap, the photochemically formed aryl radicals can be intercepted. So for example, N-methylpyrrole or similar pyrols here are well known to intercept these aryl radicals really efficiently, and so you can do these CH arylation reactions here. This works very well for a fairly broad substrate scope. And so while synthetically this is all absolutely beautiful and seems highly useful, there was some mechanistic debate that emerged over the subsequent years. There was first a comment by a group in Italy, the colleagues Gironi and Balzani from Bologna commented on some mechanistic concerns that they had, and then the Regensburg team replied to that, and then even an Australian group got involved at the very end to resolve the mechanistic questions here. So briefly, the initial mechanistic proposal involved here this photosensitizer co-catalyst couple. You start down here, you have ruthenium 2+ in the electronic ground state. This absorbs a visible photon. You have, after intersystem crossing, the triplet MLCT excited state of rupert B. And this triplet MLCT can now undergo energy transfer to pyrene, here abbreviated as PY, and you will form here triplet excited pyrene. This is a well-established reactivity of the ruthenium pyrene couple in the physical inorganic literature. If you look back at Tom Meyer's paper, they had looked at that. So this undoubtedly happens. And then the mechanistic proposal further included a reductive quenching here of that pyrene, triplet pyrene here, in such a way that the pyrene would be reduced here. That's why it's called reductive quenching. And at the same time, the tertiary amine, in this case here, the isopropylethylamine, would undergo oxidation to the cation and then be further degraded by the common reaction pathways. And then this pyrenyl radical anion is indeed thermodynamically competent for aryl bromide or aryl chloride dehalogenation, certainly for activated substrates here with these cyano groups. The reduction potential is a bit less negative than it could be for unsubstituted variants. So then ultimately this will lead to this aryl radical, and finally the interception with N-methylpyroles or other radicals will lead to the final product here. Clearly this reaction here works. The question or the criticism that came over from Italy was only that perhaps this is not the most plausible mechanism. The main concern that they put forward was of thermodynamic nature in my perception, namely that the reduction potential of triplet excited pyrene is known, and the oxidation potential of Hönig space is also more or less known. And so you can estimate the driving force for electron transfer from the tertiary amine to the triplet pyrene. And that would be energetically uphill according to their estimate by roughly 1 electron volt. And so this would be a very slow reaction at best, presumably with rate constants on the order of perhaps 10 to the 4 per molar per second, something like that. Yeah, so I see that concern, and the Regensburg team also saw it and replied to it. I'm going to come to that in a second. The criticism from Italy was not just criticism, it was also constructive in the sense that they put forward an alternative mechanism which they considered more likely to happen just on paper, not with much more at hand. So they proposed, yes, we have the triplet pyrene formation here initially, that's okay, but then they suspected that as one of the many options that are viable here or conceivable here, that 2 triplet excited pyrenes would actually undergo triplet-triplet annihilation, similar to what I'd shown you in my prior project. And then you have a singlet excited pyrene, and that singlet is now at significantly higher energy than the triplet. So this is a lot more oxidizing, sufficiently oxidizing for tertiary amines. And from there, you could then form the pyrenyl radical anion. Again, this is undisputed that this has to form. This is going to be the key catalytic species, which is going to do the final reaction. That was the take that Ceroni, Balzani, and co-worker had. And then the reply in how I read it was, yes, that's an option, but there are many other options as well, and I agree with that. And also part of the reply, in my view, was that it is very, very difficult to clarify such a mechanism here, and there may be no single, no unique mechanism in such a multi-component system. And I agree. And the Australian group here, which then also published a paper in Antwerp here, confirmed that in a way, confirmed the claim that it is very, very complicated, because they found out that the mechanism in this very system here comprised of rubipi and pyrene is yet different from that proposed by the Italian group. And before that Australian work had been published, we had already entered the game, trying to gear a system, trying to design a specific sensitizer co-catalyst system that would take us to the triplet-triplet annihilation or conversion mechanism. So by intention, by design, get to that mechanism, see whether it's viable, whether we can enforce it, whether we can see the relevant intermediates, and what we can learn from that. So we chose an iridium photosensitizer in this case, not the ruthenium photocatalyst, because that can undergo reactivity that was then confirmed by the Australians. We saw this as well. This confused us, and we turned away from ruthenium immediately. Chose iridium and then a T-butylated version of pyrene. We can talk about the reasons for the T-butyl groups later on in the discussion if there is really a need for that. So our métier is really spectroscopy, time-resolved stuff, mechanistic investigation. So we try to see each and every intermediate in this reaction cycle, and actually succeeded in doing that. So we see the triplet pyrene here in transient absorption. We can determine the rate constant for its formation from luminescence quenching experiments. That's fairly straightforward. We can observe the delayed fluorescence that is expected for the upconversion. If an upconversion mechanism is operative, you have the delayed fluorescence as a diagnostic marker observable. We can quantify the upconversion quantum yield. That's in fact the limiting performance factor of the overall system. It's about 5% here. It's not particularly good, neither particularly bad for a system in organic solution. We can also see then how the singlet excited pyrene is quenched reductively to the pyrenyl radical anion here by the sacrificial electron donor, and we have used dimethylamine here for spectroscopic reasons and not tunic space or anything else. This is a highly efficient process occurring with a very high rate constant. And then what's quite important, and particularly because also the Australian publication did not have this, we actually see the catalytically active species, the pyrenyl radical anion, directly by transient absorption spectroscopy. It's not that often that you see a catalytically active species in chemistry when you think about it. It's typically not possible in thermal reactions, and even in photochemical reactions is often quite tricky. So we then managed to monitor how the pyrenyl radical anion disappears, how it forms here, one electron reduced form of the substrate. Typically, this is a stepwise process here, the reductive dechlorination, electron transfer first, followed by release of the chloride anion here. And we see that reaction here. I'm going to show it to you now here with these transient absorption spectra. When there is no substrate present here in the left panel, You clearly see here this band at 495 nanometers. That's the pyrenyl radical anion, which has quite a long survival time here in absence of any substrate. It is still around 500 microseconds after a laser pulse. When, however, this substrate here is dumped into the solution with the substrate, you see that the pyrenyl radical anion disappears a lot faster. So after 5 microseconds, there is a bit there, but then afterwards it's gone. So this is the direct monitoring, live monitoring of the reaction here by time-resolved spectroscopy. You can, of course, also do the more straightforward thing and monitor the reaction by NMR spectroscopy. We've chosen 19F NMR here using an internal standard IS here at -119 ppm. You see here the starting material disappear, the product 1P appear here. That's the hydrodehalogenation product that forms over time here under LED irradiation again. So we're turning away from the high pulsed lasers that we use for the spectroscopic studies and then show that our combination of sensitizer, annihilator, and sacrificial electron donor does also work with LED irradiation under various conditions. For reductive dehalogenations, I think it's sufficient to show you one, and for these pinnacle couplings and also detosylation reactions do work, although rather poorly in this particular case due to lack of sufficient reducing power. So that is my take on photochemical upconversion and its use in photocatalysis. With that, I'd like to switch topic again rather drastically and now talk about the announced photo-induced hydrogen atom transfer reactivity that I announced at the very beginning. This here is quite an early study in Photoredox catalysis by Pack and co-workers. They published a series of quite nice, interesting papers in the 1980s on olefin hydrogenation, photoreduction of electron-deficient olefins here using Rubipi as sensitizer. This sacrificial donor here, PNAH here, it's a NADH analog. It's a much cheaper variant thereof, but has basically the same function in a methanolic solution. And this leads to olefin hydrogenation, presumably via a classic electron transfer, proton transfer type of mechanism. This olefin here is substituted with electron withdrawing substituents. Its reduction potential is not very negative, and so you can form this radical anion here after reductive quenching of Rubipi by BNAH. You have a 1 electron reduced ruthenium complex that is sufficiently potent a reductant to form this radical intermediate. This can be protonated. You then have this tertiary radical intermediate and then uptake of a second formal equivalent of H atom, either by a H atom transfer directly from the oxidized sacrificial electron donor or by any sequence of electron and proton transfer steps will lead to the final product. So that's, in my view, classic photoredox catalysis, single electron transfer reactivity, SET. That's the typical thing. So now here my PhD student Miriam Schreier, she looked at the system where we have some evidence that actually an olefin hydrogenation here of these geminal disubstituted olefins here does not occur via electron transfer, single electron transfer events, but rather via photo-induced hydrogen atom transfer. And there are a few compounds, POM-like compounds and others in the literature that have sparked some interest from the synthetic community. And we focused on a completely different compound, which is also quite widely known, an iridium complex here, a piano stool complex. This is iridium-free, cyclopentadienyl anion ligand here, phenanthroline, and a chloroancillary ligand. And we had looked at maybe 15 to 20 substrates in total. I am not listing them all. I am listing the ones for which the reaction worked particularly well. These are all substrates for which we have here this aryl substituent that will lead to benzylic radical intermediates, as we will see in a second. And our interest in this reactivity was primarily in finding out whether this could indeed be a photo-induced hydrogen atom transfer reaction rather than the traditional single electron transfer and proton transfer reactivities. So we began mechanistic studies here with radical clock type substrate. This particular substrate here incorporates this cyclopropyl ring here, and you could in principle anticipate this hydrogenation product where you place a hydrogen atom here at the terminal position and the other one here. But this product is not observable in NMR spectroscopy after a certain reaction time. However, you can isolate 71% of this ring opening product. And this gives us a hint that very likely this tertiary radical intermediate is actually formed in the overall mechanism at some point, though we do not observe this directly here in this experiment. This tertiary radical intermediate is known to ring open with a rate constant of roughly 10 to the 8 per second. That's why it's known as a radical clock substrate. And then after ring opening here, this position can be hydrogenated by an H atom donor. So here is a first piece of evidence. The observation of the ring opening product is the first piece of indirect evidence for the intermediacy of such a tertiary radical. Here's a second piece of indirect evidence for the same thing. What we observe is a correlation of hydrogenation product yields with the relative radical stabilities here. So for these radicals, as I mentioned in the beginning, we get consistently the best yields. These are the most stable radical intermediates. These benzylic radicals are roughly 17 kcals per mole more stable than the reference radical, the methyl radical here. And as we go here along the series, the yields decrease, and in the same series, the radical intermediate, the radical stability also decreases. So the secondary radical here is, of course, the least stable compared to these tertiary radicals. So that's another piece of indirect hint at the intermediacy of such radicals here, of neutral radicals, not single electron transfer products. Now, what we observe when performing this reaction and monitoring it over time, here this reduction of the model substrate, was that whenever we departed from the benchtop stable chloro complex here and monitored product formation, then in the first hour or so, nothing much seemed to happen. It was only afterwards that product was eventually formed that this hydrogenated compound here could be detected by NMR spectroscopy. And however, starting immediately from the hydride complex here, then the product formation began immediately at time zero. There was no lag phase, suggesting that upon irradiation over time, the chloro precursor complex is actually converted to the hydride complex, and that it is the hydride complex which is then the actual catalytically active species. And this process is known from electrochemistry. Electrochemically, in a CV setup, for example, it is possible to reduce the iridium-3 precursor by 2 electrons. This will also induce the reductive dechlorination here. Chloride is let out, and you have this intermediate here, this iridium-1 complex, which can be protonated to form the iridium-3 hydride. Electrochemically well known, well established. How about photochemically? We looked at it. We have here UV spectra of the chloro complex here, blue trace, and we see that as a function of irradiation time here, along the arrow, we have an absorption band that moves in around 440 nanometers here, the dotted traces. resembling the absorption spectrum of the green hydride complex here. And at the same time, in proton NMR spectroscopy, we obtain evidence for the hydride resonance here at minus 11.5 ppm. No evidence in the beginning because it's the chloro complex. Then photoirradiation in the presence of triethylamine over time leads to the hydride complex. So yes, multiple excitations are presumably needed to convert the chloro precursor complex to the hydride catalyst, but this is not yet the catalytically active species, because when we put the iridium-3 hydride compound into the solution along with the substrate and let it in the dark, nothing happens. So this iridium-3 hydride requires further activation by light. And this iridium-3 hydride is known to have a luminescent metal to ligand charge transfer excited state. The emission comes out at 700 nanometers. And we have now shown here by Stern-Vollmer type luminescence quenching experiments that as we add increasing amounts of triethylamine, a reductive quencher, we see here increasing quenching of the excited state. And so we hypothesize that this is a reductive quenching that will lead the system to the iridium-2 hydride intermediate, and that this is then the actual catalytically active species. So we wanted to see that. We wanted to see, like the pyrenyl radical anion in the prior chapter, we wanted to see the catalytically active species by transient absorption spectroscopy, and failed. What we see in this experiment here performed using iridium-3 hydride, triethylamine, and light is this double band absorption spectrum here, a band at roughly 600, one at roughly 640 nanometers. And these two bands coincide very nicely with a reference spectrum of this isolable iridium-1 reference compound, which I have talked about later. And we suspect what is happening here in this system is that after excitation of the iridium-3 hydride to the MLCT, there is indeed reductive excited state quenching. The species that we wanted to see is indeed formed, but it is so short-lived that it escapes our detection method. This iridium-2 hydride here is estimated to have an iridium-2 H bond dissociation free energy of roughly 45 to 50 kcals per mole. So this is a really, really weak metal hydrogen bond. So we suspect this, this intermediate here is so short-lived, immediately releases H atoms to wherever it can, that actually this intermediate cannot be detected. So very fast onward reaction. So this led us to the final mechanistic proposal shown here. If I start here with the hydride complex, then there will be excitation with light, reductive quenching by triethylamine, that's the electron source. That's the iridium-2 with the really weak metal hydrogen bond that I have just talked about. This is so reactive that we cannot observe this intermediate here. It escapes detection for kinetic reasons. Then we have hydrogen atom transfer to these geminal disubstituted olefins here. I have shown you indirect evidence for the intermediacy of these radicals here, the product radical correlations, and also the radical clock type substrate that I have shown you points towards this intermediate. The iridium-1 compound here, this is isolable, this has been known before, and this can be protonated to reinstate the initial starting material. Alternatively, you can start from the chloro precursor complex and convert it over time in a fairly slow and inefficient multi-photon excitation process into this iridium-1 precursor here that will then enter the catalytic cycle. And for preparative reasons, it is actually preferable to start from this precursor complex. It's more easy to handle than this hydride complex. Yeah, that's it. That's the story. Time's almost up here. I've talked today mostly about our endeavors in photoredox chemistry and radical chemistry. Some of you might know that we have also an interest in the development of new photocatalysts and luminophores, particularly made from earth-abundant metals. This will be for another time, including other subjects that are still ongoing in the group. I'd like to briefly acknowledge Uni Basel for funding and also the Swiss National Science Foundation and the people who did the work that you have seen today are Christoph Kerzig here, the tall guy here, second from the left here. He did the hydrated electron project and much of the upconversion work. He is now assistant professor in Mainz, Germany. Then the upconversion work in organic solution, the mechanistic work was performed by Felix Glaser here, the guy below the laser pointer now. He's a graduate student in his fourth year currently in my group. And then the last project here was performed by Miriam Schreier, who graduated roughly a year ago and is now a chemistry teacher nearby Basel. Again, many thanks, Shubik and Peggy, for having me. It was a pleasure to join this symposium.
Yeah, thank you, Oliver. Very inspiring chemistry and very nice details of mechanism and kinetics, thermodynamics. Thanks a lot. I think it will help us to understand this chemistry very well. As usual, the chemistry is very inspiring, which is clear in the Q&A section. So I do see a lot of questions, but I have one. So before I move to Q&A section, I have one very short questions. So for this reduction chemistry, for the photoreductive chemistry, it's of course very interesting, yeah. But still, we need to use stoichiometric amount of, let's say, the reductive reagent, let's say triethylamine. They are the main proton donors. What will be your thought to use or to replace them by, let's say, using water in that system? The reason I'm saying, because now you have photocatalysts that can generate, let's say, hydrogen using water. But of course, there would be a challenge, let's say, how you can take this or how you activate hydrogen in that conditions. But I just wanted to have your thought.
Yeah. I think one of the challenges that I see there immediately is that you will have to think about compartmentalization, where on the one hand, you can oxidize the water and then in a spatially separate compartment do the reduction chemistry, the organic reduction chemistry. And coupling these two redox events to one another, I personally perceive as a major challenge. And it should be tackled, but I find it very difficult.
Okay. I do see a raised hand from Jerome. Jerome, please.
Yeah, thank you for this great talk. I just have a short question on the very last mechanism. How do you think the second HIT transfer is taking place? What is the source of the second hydrogen? Is it also an iridium complex or?
That's an interesting question, Jerome. We suspect it might be the one electron oxidized form of the sacrificial donor.
Okay, so then it's coming from the alpha position to the nitrogen, probably.
Yeah, so we think that you have the iridium complex and then the triethylamine, and they react with one another. And then they are still, while they are still close and the substrate is also present, then maybe the oxidized tertiary amine can give the H atom equivalent to the radical intermediate. Photochemically, we are blind to this second step because we cannot trigger it in some synchronous fashion. You know, this will happen spontaneously, and we don't know when to detect, and other events already take place while this occurs.
Oh yeah, but maybe the deuterium labeling experiment could help. No?
Yeah, we have done it. And it's been rather laborious and relatively poorly insightful in this case. I think I forgot most of the details, but it was not fully conclusive. It's in the paper, but I apologize, I forget the details. And all I can remember is it was not conclusive.
Okay, thank you.
Yeah.
Yeah, I do see a lot of questions in the Q&A section. So the first question is from Stephanie Amos. Great talk, thanks. Why is it that the electronic decoupling leads to an increase in quantum yield? Examples with anthracene.
Yeah, in the fluorescence D-up conversion, yeah. This is a typical thing when you think about what deactivates the excited state here in this system, then it is likely a high frequency oscillation occurring on the carboxylate core. You know, here you have a CO double bonds and you have oscillations there that are fairly efficient in mediating non-radiative relaxation. And when you then take these oscillations away from the part that is actually fluorescent, when you electronically decouple, that will enhance your photoluminescence quantum yield. It's quite a general principle.
There is a second question. What is the purpose of use hydrated electron?
Yeah, they are highly reducing, of course. I find it difficult to imagine a more reducing species in the condensed phase than the hydrated electron. It's as reducing as it can be. So you can actually activate substrates with that you could not activate with other radical anions, for example.
There is a question from Tuhin Patro. Is it possible to use white light or sunlight to get both the sequential excitation?
Yes, in certain carefully selected systems, that is possible. There, one very active group in this field of upconversion is the group of Phil Castellano in North Carolina, and they have systems that operate under sunlight irradiation. This, however, requires a very, very efficient triplet-triplet annihilation upconversion. For our system, that is not the case. So those would not operate under sunlight conditions because there are simply not enough photons per unit time to promote the chemistry.
And now we have a question from Bikash Kumar. What is the importance of using photo-induced, as we know so many hydrogenation methods known?
Yeah, so the world doesn't need another hydrogenation reaction. I would fully subscribe to that statement. Our purpose here was not to do another olefin hydrogenation. Our purpose here was to perhaps show that there can be other photochemical reactivities than the traditional single electron transfer. And for this, you need a certain tool, and photochemical hydrogenation is that tool. You can look at this reaction and it will be able to tell you to some extent whether your reaction is really photo-induced hydrogen atom transfer or single electron transfer.
Then there is a question from Tushar Shingo. The second excitation is by lower energy light, 532 nanometer, whereas the first one is at 430 nanometer. So is second excitation easier, or the second excitation easy, but the second excitation should be more difficult?
Yes, the second excitation is more difficult. That is correct. The reason why we have this sequence of colors, first blue and then green, is that the blue photon is needed to excite the ground state, whereas the green photon cleanly and selectively excites the already excited state. And so then you can be sure that you're no longer exciting the ground state, because the ground state is the dominant species. You can only excite maybe 10% to the MLCT. And that makes the second excitation more difficult because you only have a small concentration. And just because the wavelength is longer here, that's just given by the spectroscopic properties of the overall system.
So there are more questions, Oliver. So the question from Stephanie Amos: from the perspective of reaction design and functional group tolerance, are there issues that can occur when performing reactions with free H radicals and hydrated electrons? In the case of the hydrated electrons, could we envisage the selective reduction of water-soluble parts of a large molecule that would be majoritarily lipophilic, that is used in late-stage total synthesis, for example?
Oh, wow. That's an interesting thought. So you would want to use the hydrated electron to react at an exposed hydrophilic group in a complex organic molecule. I suspect you can have all sorts of reduction reactions with the hydrated electron. Of course, the Birch reduction is the most famous one, but as soon as you have easy to reduce groups in your system, nitro groups or others, then of course that will be a point of attack. But the idea of exposing a certain group due to its water solubility is very elegant. But there's not more I can say in response to that.
There is another question from Bikash Kumar. Can we use electrical energy for generation of electron and hydrogen from triethylamine instead of light energy?
Well, yeah, the combination of electrochemical energy input and then photochemical input is of course very promising. I'm not sure I can comment on the specific reaction that you had in mind, but in general, I personally view this as a highly promising avenue. These multi-photon excitations tend to be inefficient because they rely on the consecutive absorption of two photons. If you can replace one photon by an electrochemical energy input, then that will be an advantage in my view.
Okay, I don't see any further question in the Q&A section. Any further question from the colleagues, from the panel members? Sorry, one very final question from Tuhin Patro. Can you comment on the tertiary butyl group in pyrene? What is the impact?
Yeah, it prevents excimer formation. You know, when in triplet-triplet annihilation or conversion, what you would like to get is a clean fluorescent excited state. And these polyaromatic hydrocarbons are, however, typically stacking in organic solution. And so whenever such stacking occurs, then there is a chance of so-called excimer formation. And instead of the high energy singlet pyrene excited state, you may then form some lower energy excimer, which is less reactive. And these pyrene substituents, they are bulky enough to actually prevent this type of aggregation.
Is there any further questions to Oliver from panel members, from the participants? Then let me join along with Bikash Kumar. So Bikash Kumar very recently replied that thanks, Professor, for very nice and informative lecture. And indeed, Oliver, that was a very inspiring, very informative lecture that you have given to us. With this information, I would also like to thank all the speakers. So starting from our day one, so that's already a very good start for the symposium. So thanks a lot to all the speakers, and particularly the speakers from Asia, because I think for Masahiro, it was quite late at night. And for us, we are still okay with the time. But I'm really thankful to all the speakers, particularly Masahiro, although it's late, Liang Nian as well. It was quite late in China, but he's still here. So thank you very much, Bukhard. Yeah, I can see Liang Nian. Thank you, Liang Nian. Thank you very much. Although it's quite late evening, but you are still here. Thank you, Bukhard. You are here. Thanks, Suzanne. So she just left. She had to join in meeting. Thank you, all of you, for your very nice, kind lecture, all the interaction with the panel members, as well as all the participants. So with this note, we would like to thank you, and then we wish you a very nice evening, and we are looking forward to see you tomorrow for the second day program.